Tonight, the first space war will not begin with a declaration. It will not begin with a fleet of warships crossing the Terminator line of the moon or a missile launch tracked across a hemisphere. It will begin the way most catastrophic things begin, quietly, plausibly, with paperwork and a press release and a malfunction that nobody can quite prove was intentional. Tonight, we are going to answer exactly what the title of this video promises. How, why, and where the first space war will begin, tracing the cold physics, the resource economics, and the political logic that make this not a question of imagination, but a sequence. That sequence starts in the orbital shell above your head, where the satellites your civilization uses to see, to navigate, to communicate, and to verify that no one has launched a nuclear weapon in the last 30 seconds, are drifting in darkness that is neither peaceful nor neutral. It moves from there to the moon, specifically to craters near its southern pole where water ice has been sitting in total, permanent shadow for 2 billion years, waiting to become the most strategically valuable substance in the solar system. It continues to Mars, where the communication delay between a colony and Earth will eventually grow long enough to make real-time command impossible, and where that mathematical fact alone will transform a settlement into a sovereign military power, whether anyone on Earth votes for that outcome or not. And it ends, or rather, it ceases to be resolvable, near Jupiter, at distances where a battle could begin and end and leave no survivors before a single distress signal completes its journey back to Earth. The further humanity moves from this planet, the more completely it inherits its own worst patterns, and the less any authority back home will be able to stop it. That is the arc of tonight's journey. And to understand where it ends, we have to begin where the first move has already been made. In the one theater of conflict most people cannot see, cannot enter, and have never been asked to think about, the orbital commons above this world, which ceased to be a neutral scientific environment the moment the first nation realized that blinding your adversary's satellites was cleaner, cheaper, and more deniable than any weapon ever fielded on the ground below. In 2007, China destroyed one of its own weather satellites with a ground-launched missile. The satellite was called Fengyun 1C. It was old, it was dying, and by any operational metric, it was worthless. What China produced by destroying it was not debris. It was a demonstration. A single kinetic interceptor traveling at closing velocities above 7 kilometers per second converted a dead weather satellite into approximately 3,000 pieces of trackable shrapnel and an estimated 100,000 fragments too small to catalog but large enough, at orbital velocities, to punch through the pressurized hull of a crewed spacecraft the way a rifle bullet passes through paper. That debris field is still up there. It will still be up there in a century. And every nation with assets in low Earth orbit received the message that was actually being sent, which had nothing to do with weather satellites and everything to do with a very simple demonstration of reach. The message was this: we can do this to yours. To understand why that message carries the weight it does, you have to understand what the orbital shell above this planet actually is. Not as an abstraction, not as a region of space, but as a physical layer of civilization that has become so deeply integrated into the functioning of modern society that its absence would not merely inconvenience the world below, it would partially collapse it. Consider what GPS actually does. Most people think of it as navigation, a blued on a screen telling you to turn left in 300 meters. That is the least important thing it does. The deeper function of GPS is time. The satellites of the Global Positioning System broadcast extraordinarily precise atomic clock signals that financial networks use to timestamp every transaction, that power grids use to synchronize alternating current across thousands of kilometers of infrastructure, that telecommunications networks use to coordinate the handoff of signals between towers. The entire architecture of modern digital commerce runs on a timing signal beamed down from orbit. Remove GPS and you do not merely lose navigation. You introduce timing errors into financial clearing systems. You desynchronize power grids. You begin to degrade the backbone of the global internet in ways that are not immediately visible, but accumulate over hours into something that starts to look like systemic failure. That is one constellation. There are others. The satellites operated by American, European, Russian, and Chinese military and intelligence agencies that monitor missile launches, track the thermal signatures of rocket plumes against the cold background of the upper atmosphere, and provide the data that gives nuclear command authorities the few minutes of warning they need to make the decision that prevents accidental escalation. Those satellites are not redundant. They are singular. There are not dozens of them covering every angle. There are specific birds in specific orbits covering specific threat corridors, and each one is a node in a network whose entire purpose is to prevent a particular kind of catastrophic misunderstanding. Blind one of them at the wrong moment. And you do not merely create a gap in coverage. You create exactly the ambiguity that nuclear deterrence theory identifies as the most dangerous possible condition, a scenario in which a nation cannot confirm whether what it is seeing on its remaining sensors is a genuine launch or a sensor artifact, and in which the decision timeline is measured in minutes. This is why orbital warfare is uniquely terrifying in a way that has no clean analogy in any previous domain of conflict. A bomb destroys what it hits. A cyber attack corrupts what it touches. A ground-launched anti-satellite weapon aimed at an early warning satellite does not merely destroy a machine. It potentially removes a last check on a civilization-ending exchange, not because either side wants that exchange, but because the absence of information in a moment of crisis is functionally indistinguishable from the information that the worst has already begun. The strategists have a name for this problem. They call it crisis instability. And the orbital shell above this planet is currently arranged in a configuration that is, from a crisis stability standpoint, nearly optimally fragile. Think of it this way. Imagine that the entire nervous system of a human body, every nerve fiber, every signal pathway, were rerouted to run through a single corridor in the spine, and that corridor were made of glass, and that every hostile actor in the world knew exactly where that corridor was and had already demonstrated the ability to shatter it. That is approximately the strategic situation of every technologically advanced nation on Earth with respect to its satellite infrastructure. The dependency is total. The vulnerability is acknowledged. The protection is, in any honest assessment, inadequate. The orbital environment that humanity has built over 70 years of spaceflight was not designed with warfare in mind. It was designed around scientific utility, commercial profit, an implicit assumption, which was always more of a hope than a plan, that the norms against attacking satellites would hold the way norms against attacking undersea cables have mostly held, through mutual dependency rather than enforced law. That assumption is now being stress-tested in ways that will define the next century of human conflict, because the nations that have developed the most sophisticated orbital dependencies are precisely the nations that have also developed the most sophisticated means of targeting those dependencies in an adversary. The United States Air Force tracks approximately 50,000 objects in Earth orbit. Of those, roughly 9,000 are active satellites. The remainder is debris, dead satellites, spent rocket stages, fragments of objects that have already collided or been deliberately destroyed, and an uncatalogued background population of smaller pieces that no ground-based radar system has the resolution to individually track, but that collectively represent a constant low-level threat to every operational spacecraft in the environment. Low Earth orbit, the band between roughly 200 and 2,000 kilometers altitude where most Earth observation, communications, and reconnaissance satellites operate, has become over the past 2 decades genuinely congested in a way that the architects of the space age did not anticipate, and that current international governance frameworks are almost entirely unprepared to manage. Into this congested, fragile, inadequately governed environment, multiple nations have now introduced dedicated counterspace capabilities, weapons and systems designed specifically to degrade, blind, jam, or destroy the orbital assets of an adversary. The taxonomy of these capabilities is worth understanding in detail, because it reveals that the space war everyone imagines, missiles streaking up from the ground to explode satellites in cinematic fireballs, is actually the least sophisticated and least likely form the conflict will take. The first category is electronic warfare. Radio frequency jamming of satellite uplinks and downlinks requires no physical proximity and leaves no debris. A ground station transmitting on the same frequency as a GPS satellite can wash out the signal for receivers in a wide geographic area without damaging the satellite itself. This is reversible, deniable, and has been practiced operationally by multiple actors, including Russia and Iran, against GPS signals in contested regions. It does not constitute an act of war under any current legal framework. It happens regularly. It is happening now, somewhere as you listen to this. The second category is directed energy, ground-based and potentially space-based lasers capable of temporarily or permanently blinding the optical sensors of reconnaissance satellites, what military planners call dazzling at lower power levels, blinding at higher ones, represent a capability that the United States has formally accused China of developing and testing. A blinded reconnaissance satellite appears from the ground to have experienced a sensor malfunction. There is no explosion, no debris, no unambiguous signature of hostile intent. The attribution problem is severe. The affected nation knows its satellite has been blinded. It cannot prove to a legal or diplomatic standard by whom. The third category is what analysts call co-orbital anti-satellites, spacecraft that maneuver close to a target satellite and remain in proximity, either to surveil it, to jam it at close range, or to physically interfere with it in ways ranging from bumping it out of its operational orbit to more direct forms of destruction. Russia has tested several of these systems openly enough that Western space agencies have issued formal statements of concern. A satellite that approaches another satellite and matches its orbit is not necessarily a weapon. It might be an inspector. It might be a servicing vehicle. It might be a weapon that has not yet been given the order to act. The ambiguity is not incidental. It is the point. The strategic value of a co-orbital interceptor lies partly in what it can do and partly in the permanent uncertainty it creates about whether it is about to do it. The fourth category, the one China demonstrated in 2007, and that Russia demonstrated again in 2021, when it destroyed its own Cosmos 1408 satellite in a test that forced the crew of the International Space Station to shelter in their docked Soyuz capsule, is direct descent kinetic kill, a missile launched from the ground, accelerating a small kinetic impactor to orbital closing velocities, collides with a target satellite and converts it into a debris field. This is the blunt instrument of counter-space warfare, the option that is hardest to deny and most catastrophic in its secondary effects, because the debris it generates does not respect the nationality of the satellites it subsequently threatens. A debris field generated at 800 kilometers altitude will intersect the orbits of every satellite operating in that altitude band, from every nation for decades. This is where the concept that physicist Donald Kessler described in 1978 becomes not merely a scientific concern, but a strategic one with implications that redefine what deterrence means in orbit. Kessler's insight was elegant and devastating. Once the density of objects in a particular orbital band crosses a certain threshold, collisions between those objects generate debris faster than atmospheric drag clears it, creating a self-sustaining cascade that progressively fills the orbital environment with lethal fragments until that altitude band becomes operationally unusable. The cascade is self-reinforcing. Each collision produces debris. That debris produces more collisions. Those collisions produce more debris. The process, once initiated above the critical density threshold, cannot be stopped. It can only be inherited by whatever civilization comes afterward. For most of the history of the space age, Kessler syndrome was understood as an accidental risk, the consequence of negligent debris management, of leaving dead satellites in orbit, of allowing rocket stages to linger in congested bands. What has changed in the past 15 years is the growing recognition among military strategists that Kessler syndrome can also be a weapon, an actor willing to sacrifice its own orbital assets, willing to accept the degradation of its own satellite constellation as an acceptable cost, could, in principle, initiate a Kessler cascade at a strategically chosen altitude that would deny that orbital band to every other actor for generations. It is, in the most precise sense, a scorched earth strategy applied to space. You do not need to win the orbital environment. You only need to be willing to destroy it for everyone. The parallel to nuclear deterrence is uncomfortable but exact. Mutually assured destruction worked. To the extent that it worked, because both sides understood that initiating a nuclear exchange would result in the destruction of the initiating party as well as the target. The deterrent logic of Kessler's weapon has a similar structure, but with a crucial and deeply disturbing difference. The cost of the initiating party is degraded commercial and military satellite services. The cost to an adversary more dependent on those services is potentially catastrophic. The asymmetry between a nation willing to absorb orbital degradation and a nation whose military command and control architecture relies absolutely on satellite communications creates exactly the kind of coercive leverage that strategists spend careers looking for. If you need the orbital environment to function and your adversary is willing to destroy it, your adversary holds the initiative. The more dependent you are, the more you are deterred from any action that might provoke the cascade. This is the invisible geometry of the conflict that is already underway above this planet. Not explosions, not declarations. A slow, careful accumulation of capabilities, demonstrations, and positional moves in an environment that most of the population of Earth never thinks about and cannot see, conducted by states that understand, with complete clarity, that the nation which achieves meaningful dominance in orbit will hold a form of leverage over every other nation that has no historical precedent. Not the leverage of nuclear weapons, which are so catastrophic that their use is self-defeating. The leverage of infrastructure, of the ability to selectively degrade the nervous system of a modern civilization while maintaining plausible deniability and remaining, technically, below the threshold of an active war. And all of this, the jamming, the dazzling, the co-orbital stalkers, the kinetic interceptors, the Kessler calculus, all of it is confined to a thin shell extending perhaps 2,000 kilometers above the surface of a single planet. It is the opening paragraph of a story whose later chapters are written across the entire solar system, because the logic that drives states to contest orbital space above Earth, control the high ground, deny the adversary the infrastructure they depend on, seize the resources that will define the next century of power, does not stop at 2,000 kilometers. It does not stop at the moon. It follows human beings wherever they go, as reliably as gravity, as inevitably as atmosphere follows a planet massive enough to hold it. The next contested frontier is not in orbit. It is 400,000 kilometers away, in a darkness so complete and so ancient that the light which last touched it was falling on a planet that had not yet evolved anything capable of fighting over it. The moon has water, not liquid water. Nothing on the lunar surface exists in a form a human being could drink without industrial processing. But in the permanently shadowed craters near the lunar poles, craters whose geometry is so deep and whose position is so precise that the sun's rays have not reached their floors since the solar system was young, water ice exists in concentrations at multiple spacecraft. India's Chandrayaan-1, NASA's Across Impactor, the Lunar Reconnaissance Orbiter, have confirmed beyond serious scientific dispute. The Shackleton Crater near the lunar South Pole, the Hayworth Crater, the No-Beal Crater, cold traps that have been accumulating volatile compounds delivered by cometary impacts over billions of years, preserving them in darkness at temperatures approaching negative 200 degrees Celsius, waiting. What they are waiting for, it turns out, is us. The strategic value of that water ice cannot be overstated, and it flows from a single fact of rocket chemistry that determines the cost of everything humanity will ever do in space. Water, H2O, can be electrolyzed into hydrogen and oxygen. Liquid hydrogen and liquid oxygen, when combined in a rocket engine, produce the highest specific impulse of any chemical propellant system we have yet developed, which means that water ice on the moon is not just water, it is rocket fuel. It is the ability to launch spacecraft from the lunar surface without lifting every kilogram of propellant from the bottom of Earth's gravity well, a journey that currently costs, depending on the launcher, between $2,000 and $10,000 per kilogram. A propellant depot on the moon, fed by water ice mined from permanently shadowed craters, transforms the economics of everything beyond low Earth orbit. Missions to Mars, stations at the Earth-Moon Lagrange points, deep space exploration, all of it becomes dramatically cheaper and faster if you do not have to carry your fuel up from Earth. This is why When the major spacefaring nations of the 21st century look at the moon, they do not see a dead rock. They see a gas station at the top of a gravity well. And they are, right now, in the early stages of a competition to determine who will own it. The American Artemis program has established a series of bilateral agreements with partner nations, the Artemis Accords, that articulate a framework for lunar resource utilization based on the principle that extraction of space resources for use does not constitute national appropriation of the moon itself. This is a careful legal construction designed to permit commercial and governmental mining of lunar water ice and other resources without technically violating the 1967 Outer Space Treaty, which prohibits national sovereignty claims over celestial bodies. The logic is that you can own the water you extract without owning the crater you extracted it from, in the same way that a fishing nation owns the fish it catches without owning the ocean. China and Russia have not signed the Artemis Accords. They have instead pursued their own bilateral framework, the International Lunar Research Station Program, which envisions a permanent Chinese-Russian presence on the lunar South Pole on a timeline that overlaps almost precisely with the American Artemis landing schedule. Both programs are targeting the same region of the moon. Both programs understand that the permanently shadowed craters in that region represent a finite and extraordinarily valuable resource. Neither program has any binding legal mechanism to resolve a territorial dispute if their infrastructure ends up in proximity and their interests end up in conflict. The 1967 Outer Space Treaty, the foundational document of international space law, drafted in a period when the moon was an aspiration rather than a destination, does not contain an enforcement mechanism. It contains a prohibition on weapons of mass destruction in orbit and on celestial bodies. It contains a principle of the moon as the common heritage of mankind. It does not contain a process for resolving competing claims over a specific crater that both a Chinese mining operation and an American water extraction facility would like to use as the anchor point for their propellant infrastructure. It does not contain a tripwire. It does not define with any precision what act would constitute a hostile one. This legal vacuum is not an oversight. It is a predictable consequence of drafting space law before the stakes were real enough to force genuine compromise. Now the stakes are becoming real, and the compromise has not been made, and the parties whose interests are most directly in conflict are the same parties whose broader geopolitical relationship is characterized by strategic competition across every other domain: technological, economic, military, and ideological. The first conflict over lunar resources will almost certainly not be announced as a conflict. A mining robot that strays into a disputed area of a crater rim and is remotely disabled will be described as a technical malfunction. An access road graded across the approach corridor to a rival nation's proposed landing site will be described as routine infrastructure development. A communications blackout affecting a rival nation's surface assets will be attributed to solar weather. The early phases of a resource conflict in a domain with no enforcement authority and no agreed definitions of hostile action look, from the outside, like a series of unfortunate accidents and misunderstandings, right up until a moment when the accumulated weight of those accidents and misunderstandings produces a response that cannot be characterized as anything else. That moment, that threshold crossing, is what the permanently shadowed craters of the lunar South Pole are quietly waiting to host. Not in some distant speculative future. Within the operational planning horizons of programs that are currently funded, currently staffed, and currently scheduled to put human beings and robotic infrastructure within a few kilometers of each other on a body 400,000 kilometers from the nearest court, the nearest mediator, and the nearest authority capable of enforcing anything at all. The moon is close enough to Earth that a radio signal crosses the distance in about 1.3 seconds. Close enough that the nations competing for its resources are still operating under the psychological assumption that Earth's rules, Earth's laws, and Earth's diplomatic frameworks will somehow extend to cover what happens there. That assumption will hold, perhaps through the early phases of lunar development. It will hold as long as the stakes remain low enough that no party calculates the value of the resource worth more than the cost of the confrontation required to secure it. But the calculation changes. It always changes. And when it does, When the first permanent cislunar infrastructure makes water ice not a scientific curiosity, but an operational necessity. When the first repellent depot makes a difference between a mission that succeeds and a mission that fails. When the first nation decides that its presence on the lunar South Pole is a strategic interest it is prepared to defend. The question will no longer be whether the first space conflict begins in cislunar space. The question will only be what form it takes, and how quickly the parties involved discover that none of the frameworks they brought from Earth were designed for the environment they are standing in. And if that realization is sobering when applied to the moon, a body that sits close enough to Earth that you can see it with the naked eye, that a radio signal crosses in a heartbeat, that a spacecraft can reach in 3 days, then consider what it becomes when applied to the next world out. A world where the distances are not 400,000 kilometers, but 80 million, where the communication delay is not 1.3 seconds, but 20 minutes, where a colony once established cannot be resupplied on any schedule shorter than 26 months, where the physics of the environment do not merely complicate Earth's authority over what happens there. They make that authority, in any operationally meaningful sense, mathematically impossible. We are going to Mars. That sentence carries the casual confidence of a species that has not yet fully reckoned with what it means. We say it the way the first Polynesian navigators might have said we're going to Horizon, as a declaration that will strip clean of the oceanic distances, the months of open water, the absolute severance from anything that could help if something went wrong. We say it in press releases and funding documents and documentary titles and the speeches of billionaires standing in front of rocket fairings. And in saying it, we unconsciously import with us every assumption that proximity still licenses, that help is reachable, that authority is meaningful, that the decisions made in a moment of crisis can be reviewed, overruled, or corrected by someone with a perspective and the power to do so. The physics of Mars will dismantle those assumptions one by one, with a thoroughness that is not cruel so much as it is simply indifferent. Begin with time, not the subjective time of a long voyage, the tedium of 6 to 9 months in a pressurized cylinder, the psychological weight of watching the Earth shrink to a point of light, and then to nothing distinguishable against a background population of stars. Begin instead with the time that governs the relationship between Mars and everything that supplies it. The Hohmann transfer orbit, the fuel-efficient elliptical trajectory that arcs a spacecraft from one planet's orbit to another's, using the sun's gravity as the primary engine and propellant as the nudge, is not a convenience. It is an orbital mechanical constraint as rigid as the shape of the planets themselves. A spacecraft departing from Mars can only do so efficiently during a narrow launch window that recurs every 26 months, when the geometry of Earth's and Mars's orbits aligns to make the journey possible without requiring a quantity of propellant that would make the mission economically catastrophic. Miss that window and you wait. There is no alternative timeline, no emergency departure option, no express route you can purchase with additional resources. The planets move on their own schedule, and the Hohmann transfer window opens and closes on a cadence that the first Martian colonists will feel not as an astronomical abstraction, but as the pulse of their own survival. Consider what this means in practice for a colony that has not yet achieved self-sufficiency, and for the first decade or two, no colony will have. Every supply ship that arrives brings with it the material continuity of the settlement, medical supplies, replacement components for life support systems whose failure modes are not all predictable, seeds and growing media and agricultural technology, electronics, the specific industrial chemicals that a colony cannot yet synthesize locally. All of it loaded into cargo manifests and launched during the window, and then committed to the void for 6 to 9 months of transit in which nothing can be added, nothing retrieved, and no change in the manifest is possible regardless of what happens at the destination in the intervening time. An illness breaks out in month 4 after the last supply ship departed. An essential atmospheric recycling component fails in month 7. The colony's hydroponic system collapses in month 12. The next ship is 14 months away. It was loaded 11 months ago. It does not contain the specific item now needed, because no one knew to include it when the manifest was finalized, because the problem had not yet occurred. The ship cannot be recalled. It cannot be redirected. It is a message written in the past, traveling through vacuum, addressed to a future that has already changed in ways the message has no way of accounting for. Now translate that logistical reality into the language of conflict, and what you discover is that a Martian siege, a deliberate effort by some actor, terrestrial or otherwise, to cut off or compromise the supply line between Earth and a Martian colony, does not look like the sieges of medieval history. It does not require surrounding walls and denying exit. It requires only the disruption of a single launch window, a hostile power that could prevent supply ships from departing Earth, or intercept them in transit, or damage them sufficiently during the vulnerable phases of departure and arrival, would not need to engage the colony directly. It would not need to win a battle. It would need only to wait. The colony would begin to die, not from violence, but from the slow arithmetic of consumption exceeding replenishment. Food runs out before ammunition does. Oxygen recycling degrades before weapon systems do. The most devastating weapon in an interplanetary siege is not a kinetic impactor or a directed energy beam. It is a calendar. The 26-month heartbeat of the Hohmann window transforms every conflict near Mars into a war of logistics rather than a war of firepower. And in a war of logistics, the party with the shortest supply line wins. This is a principle as old as organized warfare. Napoleon understood it. Sherman understood it. What neither of them could have anticipated is a version of that principle applied across tens of millions of kilometers of vacuum, where the supply line is not a road or a rail line that can be repaired but an orbital trajectory that is mathematically fixed, where the convoy cannot accelerate to avoid interception, because its fuel budget was calculated to the kilogram before it left, and where the distance between departure and arrival is so vast that a threat launched years in advance. A single interceptor placed on a crossing trajectory with precisely calibrated timing can blindside a cargo convoy that had no way of detecting it before the moment of impact. The vulnerability of deep space supply lines is not a tactical problem with a tactical solution. It is a structural feature of the physics. A cargo ship traveling from Earth to Mars spends a better part of a year in the interplanetary medium, which sounds like a description of open space, serene and empty, but is more accurately understood as a corridor with no cover, no shelter, no speed advantage, and no ability to deviate meaningfully from its planned trajectory without expending propellant reserves that are not there to be expended. It broadcasts its position not through any transmission, but through the geometry of its orbit. An observer who knows when it departed and what trajectory was assigned, and that information is not secret, because departure windows are public and trajectory calculations are reproducible by any party with basic astrodynamics capability, can calculate with high precision where that ship will be at every moment of its 6 to 9 month transit, not approximately, precisely, within margins that make interception not a feat of detection, but a feat of planning. A threat does not need to launch in response to a convoy's departure. It can launch years in advance, placed on trajectory that will intersect the convoy's path at a calculated point far from either planet, in a region of space where no rescue is possible and no help will arrive before the calculation completes itself. The attacking object requires no guidance system sophisticated enough to track and pursue a maneuvering target, because the target is not meaningfully maneuvering. It requires only sufficient accuracy in the initial trajectory calculation to achieve an intercept within a margin that terminal guidance or a simple proximity fuse can close. The technology is not exotic. The precision is not unprecedented. What makes it devastating is not its sophistication, but its timing. The 6 to 9 month gap between when a threat could be detected and when it completes its mission, during which the convoy has no ability to return to Earth, no ability to proceed to Mars in any timeline shorter than the transit already underway, and no ability to do anything other than continue along the corridor that was calculated before the threat was known to exist. The people who plan logistics for a Martian colony in any period of geopolitical tension will understand this. They will plan for it. They will think about convoy dispersal and redundant manifests and emergency caching strategies on the Martian surface. They will think about it the way naval strategists in the Atlantic thought about U-boat corridors during the Second World War. mapping the geometry of vulnerability, and trying to route around the places where the math of interception was most favorable to an adversary. But the interplanetary medium does not have the geographic diversity of an ocean. There is no alternate route to Mars that bypasses the Hohmann geometry. There is only the window, and the corridor the window creates, and the 6 to 9 months of exposure that no amount of planning can eliminate. The surface they are protecting supply lines to is itself an environment that defeats most of the military assumptions that Earth-trained planners will arrive with. Mars as an atmosphere. This is the first thing most people know about Mars that is technically true and practically misleading, because the word atmosphere imports a set of associations from the only planetary atmosphere most human beings have ever experienced, a dense, moist, acoustically conductive medium that carries sound, generates weather in patterns a human body can survive without special equipment, and is thick enough that a projectile moving through it experiences significant deceleration through aerodynamic drag. The Martian atmosphere does carry sound. It does generate weather. Projectiles moving through it do experience some drag. But the atmosphere of Mars is approximately 0.6% as dense as Earth's at sea level, roughly equivalent to the pressure found in Earth's stratosphere at an altitude of about 35 kilometers. This is not, in any meaningful tactical sense, an atmosphere. It is a statistical presence, a ghost of a medium. What this means for explosive ordnance is both counterintuitive and, once understood, deeply unsettling. An explosion on the Martian surface produces a pressure wave, as all explosions do, but in an atmosphere 170 times less dense than Earth's. That pressure wave dissipates with a speed and completeness that eliminates the concussive effects that make terrestrial explosions lethal at distance. An artillery shell detonating in the open on Mars produces a flash, an intense but rapidly contained thermal pulse, and fragments traveling outward at velocities that the thin atmosphere decelerates only minimally. What it does not produce, cannot produce, is the acoustic shock wave that would rupture lungs and shatter structures at 50 or 100 meters on Earth. The lethal radius of a given explosive charge on Mars is defined almost entirely by fragmentation, not by overpressure. The killing is done by shrapnel, not by the blast itself. There is a secondary implication that is stranger and more viscerally disturbing. An explosion on Mars, observed from outside the immediate fragmentation radius, is silent, not quiet, silent. The atmosphere is too thin to carry sound at any operationally meaningful distance. The thermal flash arrives at the speed of light. The fragments arrive on their ballistic trajectories. But the sound of the detonation, the crack and rumble that the human nervous system has evolved over millions of years to use as warning, as orientation, as a signal that something violent has happened nearby. That sound either never reaches an observer at all, or arrives as a faint whisper so attenuated by distance and atmospheric thinness as to be functionally indistinguishable from the ambient noise of the wind. Combat on Mars, at any range beyond the immediate fragmentation envelope of a given weapon, is conducted in a silence that is no analog in any historical battlefield. There is no acoustic horizon. There is no sound of an incoming round, no supersonic crack of a bullet's passage, no distant rumble of artillery that tells a unit commander that something is happening in a given direction and at a rough distance. There is only the visual domain, and in an environment where dust storms can reduce visibility to meters and where the same rusted, ochre-red topography extends in every direction with a sameness that defeats human spatial intuition evolved for Earth's visual variability. The loss of the acoustic channel is not a minor inconvenience. It is a removal of half the sensory apparatus that military training across all of human history has been designed to exploit. The dust is its own operational constraint, and its scale on Mars is something that terrestrial military planners have not fully internalized because it has no terrestrial equivalent. The Martian dust storm season is not a periodic nuisance. It is a planetary-scale weather event. In 2018, a global dust storm, the kind that recurs on Mars every few Martian years, though not on a perfectly predictable schedule, grew to envelop the entire planet for months. Not a regional storm, not a continental system. A planetary shroud of suspended fine-grained regolith that reduced solar irradiance at the surface to a small fraction of its nominal value, grounded every solar-powered surface asset, and reduced surface visibility in the affected regions to near zero. The Opportunity rover, operating on solar power, was unable to recharge its batteries for the duration of the storm and never recovered. An army operating on Mars during a global dust storm cannot fly. Its solar-powered equipment loses its energy source. Its optical targeting systems lose their ability to acquire targets at distance. Its thermal management systems face a radically changed energy budget. The insulating effect of suspended dust in the upper atmosphere can actually raise nighttime surface temperatures while lowering daytime insolation, producing temperature swings and thermal gradients that stress materials in ways that compound over operational timescales. A dust storm on Mars does not merely inconvenience a military campaign the way a severe winter inconveniences ground operations in Central Europe. It potentially freezes an entire theater of operations for weeks or months at a time, creating a kind of enforced operational pause that an adversary with better thermal power sources, nuclear rather than solar, could exploit as a decisive asymmetric advantage. The Martian environment, taken as a whole, does not merely modify the tactics of warfare the way jungle, desert, or Arctic conditions modify the application of terrestrial military doctrine. It creates a tactical environment that has no precedent in human military experience, and into which the lessons of every previous war transfer only partially, and with significant risk of catastrophic misapplication. The silence removes acoustic warning. The thin atmosphere removes concussive effect. The dust removes visibility and solar power. The gravity, 38% of Earth's, alters the ballistic trajectories of every projectile in ways that trained Earth soldiers will initially miscalculate. The sealed habitat requirement means that any breach of a structure, any puncture of a pressurized module, is not merely structural damage, but an immediate life-threatening emergency that requires a response regardless of what is happening outside the structure. This last point deserves particular attention because it transforms the tactical calculus of attacking and defending a Mars base in a way that has no clean parallel in any terrestrial analogy. On Earth, a building under fire can be abandoned. Personnel can withdraw, seek cover, regroup. The building may be important. It may contain equipment or command infrastructure or supplies, but the people inside it are not, by the physical fact of being inside it, dependent on it for their next breath. On Mars, a habitat under attack cannot simply be abandoned. The suit-up time required to transition from shirt-sleeve environment to EVA suit is measured in minutes that may not be available. Personnel inside a pressurized module that is losing pressure to a penetration or partial collapse are not in a tactical situation. They are in a survival emergency that subsumes every other consideration that demands immediate response, and that an adversary could exploit with ruthless efficiency by targeting not the weapon systems, not the command center, not the food stores, but the habitat itself. The simplest possible attack on a Martian base is also potentially the most devastating. Not a precision strike against military infrastructure, but a strike designed to force a pressure emergency that consumes the attention and resources of every person in the base simultaneously, that transforms defenders into emergency response personnel, and that could be executed at a level of technical sophistication far lower than what would be required to defeat a competent military force in open combat. The people living in that environment will have known this from the beginning. They will have designed their habitats with redundancy and blast shielding. They will have developed emergency protocols and maintained them with a discipline that living in a place that will kill you in minutes if the walls fail tends to produce. They will have built, over years and decades of settlement, a relationship with the physical environment of Mars that no military force dispatched from Earth, however well-equipped and extensively trained in simulated Martian conditions, can fully replicate. And in that knowledge asymmetry between people who know Mars from the inside and people who know it from training lies one of the most consequential military dynamics of any future Martian conflict. But there is something more fundamental even than environmental knowledge. There is time. The one-way light travel time between Earth and Mars varies continuously as the two planets move through their orbits. At closest approach, opposition, When Mars is directly opposite the Sun from Earth, the distance narrows to roughly 54 million kilometers, and the communication delay falls to approximately 3 minutes. At maximum separation, when Earth and Mars are on opposite sides of the Sun, the distance stretches to nearly 400 million kilometers, and the delay reaches roughly 22 minutes. The operational average, over the full orbital cycle, hovers around 10 to 13 minutes one way, 20 to 26 minutes for a question to travel to Earth and an answer to return. This is not a technical inconvenience that better communications technology can solve. No communications technology can transmit information faster than light, because no information can travel faster than light. This is not an engineering limitation awaiting a breakthrough. It is a law of physics as foundational as the conservation of energy, and applies to every command signal, every tactical update, every request for instructions, and every authorization from authority on Earth to forces on Mars. A commander on Earth who issues an order to Martian forces will wait a minimum of 26 minutes, at best, for any confirmation that the order was received, much less executed. In a tactical situation that evolves over minutes, this delay is not a limitation. It is an impossibility. Real-time command from Earth is, in the most mathematically precise sense of the word, impossible on Mars. The consequences of this fact begin in the domain of military command and control, but they do not stay there. They propagate outward through every dimension of how a Martian colony relates to the authority structures of the Earth it came from. A local commander on Mars, a military officer, a colony administrator, the head of security for a corporate settlement, must make every time-sensitive decision without the possibility of consulting Earth, not without the luxury of consulting Earth. The way a field commander might not have time to escalate a decision up the chain of command before acting, without the physical possibility. A threat that emerges and must be responded to within 20 minutes cannot wait for Earth's guidance, because Earth's guidance, even if Earth were watching in real time and responded instantaneously, would arrive after the situation had already resolved itself one way or another. This produces a structural condition in which local commanders on Mars hold de facto authority over every decision that matters. Every decision that must be made faster than the light travel time allows consultation, which is to say, nearly every decision that a conflict would produce. De facto authority, exercised long enough and in consequential enough circumstances, does not remain merely de facto. It becomes identity. It becomes expectation. It becomes the lived reality of community that has, over years of operating at the edge of the communication window, developed its own judgment, its own priorities, its own understanding of what serves the settlement's interests, which may or may not align with what Earth's political or corporate authorities believe those interests to be. A colony that has been making its own decisions for a decade, under the mathematical necessity imposed by the speed of light, is not a colony that is waiting for Earth's permission to continue doing so. It is a community that has already become accustomed to the weight of its own sovereignty, even if no one has yet used that word. This is not a political philosophy. It is a physical process. The same communication delay that prevents real-time command also prevents real-time oversight, real-time accountability, and real-time enforcement of any rule, regulation, or directive that Earth authorities might wish to apply to Martian activities. An Earth government that orders a Martian colony to cease some activity will have its order arrive 22 minutes late at best. The colony's response, acknowledgement, compliance, refusal, or silence will take another 22 minutes to return. The entire enforcement mechanism of any authority is predicated on the ability to observe, respond, and escalate in a timescale that bears some relationship to the timescale on which the regulated behavior occurs. When that relationship is severed by a minimum 44-minute round-trip communication delay, the enforcement mechanism does not become slow. It becomes theoretical. What this means practically is that the political independence of a Martian colony is not an aspiration its inhabitants need to fight for in the conventional sense. It is a condition that the orbital mechanics of the solar system will deliver to them whether they request it or not, whether Earth consents to it or not, and whether anyone on either world is ready for the implications. The first generation of Martian colonists may arrive with full intention of remaining loyal subjects of whatever nation or corporate entity funded their passage. By the second generation, that loyalty will have been tested and transformed by years of decisions made, without Earth's involvement, by a relationship with an environment that Earth cannot fully comprehend from a distance, and by the growing recognition that the entity they were theoretically loyal to cannot protect them, cannot command them in any operational sense, and cannot prevent them from doing what they believe is necessary for their survival and the survival of their community. The third generation will not remember the transition as a political event. They will remember it the way most people remember the political arrangements they were born into, as simply the way things are. But the transition will not be peaceful simply because it is inevitable. History contains almost no examples of metropolitan powers acknowledging the sovereignty of colonial developments without attempting to resist that acknowledgement, regardless of how logistically untenable the resistance is. The British Crown did not gracefully concede the independence of the American colonies on the grounds that the Atlantic Ocean made governance impractical. It sent armies, and the armies failed, and the failure was partly logistical and partly military, and partly a consequence of fighting people who understood the terrain better than the forces sent to subdue them. The parallel to a Martian independence conflict is imperfect in detail, but coherent in structure, with the crucial difference that the Atlantic Ocean is crossable in days, and the interplanetary medium is crossable in months, and that the cost of projecting military force to Mars is not merely high, but potentially prohibitive for any but the most technologically and economically advanced state, and only then under favorable launch window conditions. This logistical asymmetry does not prevent conflict. It shapes the form it takes. An Earth-based authority attempting to coerce a Martian colony into compliance faces a fundamental problem. Every asset it sends, troops, equipment, weapons, supplies, must travel through the same Hohmann corridor that makes the colony's resupply so vulnerable. Those assets must be committed months before they arrive. Their trajectory, like that of any cargo convoy, is calculable by any party with basic astrodynamics capability. They travel through the interplanetary medium with the same exposure, the same vulnerability to prepositioned threats, the same inability to deviate meaningfully from their planned trajectory that characterizes every other object that makes the journey. A Martian colony that becomes aware of an incoming military force, which it will, because the departure window is public and the trajectory is reproducible, has 6 to 9 months to prepare. It has time to cache supplies, to reinforce habitats, to position whatever defensive assets it has developed, and to make the calculation that any military commander makes when assessing the cost-exchange ratio of a conflict, whether the force coming for them is large enough and well enough supplied to overcome the accumulated advantage of local knowledge, environmental familiarity, and the structural impossibility of the attacker receiving tactical guidance from Earth in real time. The force that arrives at Mars after a 6 to 9 month transit arrives exhausted, with supply reserves calculated for the mission as originally planned, unable to receive tactical updates from Earth in any operationally meaningful timescale, and facing an adversary that has had months to prepare for its arrival. The force that is already on Mars faces the inverse conditions. It knows the terrain in a way that only years of living in a place produces. Its command and control is local, and therefore real-time in the tactical sense that matters. Its supply chain, however strained, does not have a 6 to 9 month resupply lag for the next window. It has the existing stocks it has spent months accumulating. This is not a situation that automatically favors a defender in every scenario, but it is a situation that imposes costs on the attacker that have no easy mitigation. Into this tactical environment, there is one capability whose physics are worth understanding with particular care, because they represent the most devastating available option for a force that cannot afford a prolonged campaign on the Martian surface. Kinetic bombardment, the acceleration of dense, inert projectiles to high velocity and their delivery onto a target from orbit or from deep space, is not new as a concept. It has been discussed in military circles since the 1950s, applied to Earth in theoretical weapon systems that were never built but never fully abandoned. On Earth, kinetic projectiles face significant deceleration as they pass through the dense atmosphere, and the practical implications of this deceleration have always complicated the calculus of kinetic strike weapons. A kinetic impactor targeting a hardened underground facility on Earth must carry sufficient mass and velocity to survive atmospheric entry, with enough energy remaining to destroy the target. And the atmospheric interaction generates so much heat that the projectile must be designed to resist ablation, a design challenge that pushes against the mass constraints that determine how many such weapons can be fielded. On Mars, the atmospheric problem nearly disappears. In an atmosphere 0.6% as dense as Earth's, a kinetic impactor entering from orbit experiences deceleration that is, in practical terms, trivial. An iron rod of 10 kilograms, accelerated to 3 kilometers per second relative to the Martian surface, a velocity achievable with relatively modest propulsion systems, arrives at the surface having lost almost none of its energy to atmospheric drag. The kinetic energy delivered on impact is approximately 45 megajoules. To contextualize that number, a standard artillery shell from a 155mm howitzer delivers roughly 10 megajoules of combined kinetic and chemical energy. A Hellfire missile, the precision strike weapon used by military aircraft and drones, delivers roughly 5 megajoules of energy in its warhead. The 10-kilogram iron rod, delivered from orbit at 3 kilometers per second, delivers 9 times the energy of a Hellfire missile with no warhead, no explosive chemistry, no fusing system, and no technical signature in its descent that distinguishes it from a meteorite until a moment of impact. The crater produced by such an impact, on a world with no oceans to absorb shock waves, no deep hydrosphere to dampen seismic propagation, and a crust that transmits ground shock with an efficiency significantly greater than wet, sediment-laden terrestrial geology, would be accompanied by a seismic pulse capable of damaging structures for hundreds of meters in every direction. A habitat, even a heavily reinforced one, subjected to a ground shock of this magnitude faces failure modes that conventional blast shielding is not designed to address. Blast walls absorb overpressure from chemical explosions. They do not absorb the ground deformation produced by a 10-kilogram iron rod impacting the surface 60 meters away at 3 kilometers per second. And here is the aspect of this capability that renders it strategically different from any comparable weapon in the terrestrial military inventory. The projectile, once launched from orbit, announces itself through the physics of its entry. On Earth, an incoming kinetic impactor will be tracked by the same radar networks that monitor ballistic missiles, and the detection will provide warning. Seconds perhaps, but warning. On Mars, there are no such networks, at least not in the early phases of human settlement. There is no planetary ballistic missile early warning system. There is no radar fence at altitude capable of acquiring a fast-moving object and correlating it against a threat library and issuing a warning in time for anyone below to take protective action. The first indication that a kinetic strike has been launched may be the impact itself, or the observation, from a surface telescope or orbital asset, of the impactor on its final approach, with perhaps tens of seconds of warning before the energy is delivered. The projectiles themselves cost almost nothing in the context of the operations that would employ them. They require no explosives, no sophisticated electronics, no special materials beyond a dense, reasonably impact-resistant metal. Their effectiveness is derived entirely from kinetic energy, which is a function of mass and velocity. Two parameters that orbital mechanics can provide through periapsis lowering and deorbit burns rather than through expensive propulsion systems. A force in Mars orbit that has even modest propulsion capability has access to a kinetic strike capability that can reach any point on the surface in the time it takes the impactor to descend from its release altitude. The combination of factors that converges on Mars, the supply line vulnerability defined by the Hohmann window, the environmental hostility that degrades every imported assumption about how conflict works, the communication delay that makes Earth's authority operationally irrelevant, the physical inevitability of colonial sovereignty, and the devastating physics of kinetic bombardment in a near-vacuum world with no oceanic shock absorption, does not merely complicate the prospect of conflict. Near Mars, it creates conditions in which conflict, once initiated, would be prosecuted with brutality of physics that exceeds almost any terrestrial analogy. A war on Mars would be a war where the atmosphere cannot carry the sound of incoming fire, where the horizon is closer than it looks, and the dust can reduce it to nothing at all, where every shelter is also a life support system, and every life support system is therefore a target, where the side that runs out of oxygen loses before the side that runs out of ammunition, where supply convoys sailing through the interplanetary medium are defenseless for the better part of a year at a time, where rocks falling from the sky carry nuclear-level energy and require no fuel, no warhead, and no sophisticated electronics to deliver it, and where the commanders making decisions about all of this cannot wait for guidance from the entities that sent them, because the guidance cannot travel faster than light, and the situations cannot wait for the speed of light. This is not hyperbole. It is orbital mechanics and atmospheric physics and the law of conservation of momentum, arranged by the architecture of human ambition into something that deserves to be called what it is: the most severe military environment in the history of the species, waiting on the other side of the journey that humanity is already planning. The settlements that survive it, if they survive it, will not emerge as extensions of the nations that launched them. They will emerge as something the solar system has not yet seen, a civilization that learned to exist in an environment where Earth's rules did not apply, Earth's authority could not reach, and Earth's protection could not arrive in time. A civilization formed, as all civilizations ultimately are, by the specific physics of the place where it made its home. And what that civilization will have learned in the dust storms and the silence and the orbital arithmetic of the 26-month window is that the distance between worlds is not merely a journey. It is a transformation. What Mars produces, in other words, is the first human society for which the distance from Earth is not a temporary condition to be bridged with better technology and faster ships, but a permanent structural feature of its existence. The light-minute delay is not a communications problem awaiting a solution. It is a defining fact of what it means to be Martian rather than terrestrial, a distinction that will become more consequential, more politically charged, and more militarily significant with every generation that is born on the red world without reference to the blue one. And if that distance, the gap between a world where the sun rises in the east and sets in the west in 24 hours, and a world where the day is 39 minutes longer and the sky is the color of old rust, is enough to produce a civilization that Earth can neither command nor fully comprehend, consider what happens when the distance grows further still. Not the 80 million kilometers of close approach, not the 22-minute maximum delay of an outer opposition, but the hundreds of millions, the billions of kilometers that separate the inner solar system from the gas giants and the frozen worlds beyond them. Light minutes stretch to light hours. The round-trip communication delay that makes Earth's authority over Mars operationally impossible grows to 4 hours, 8 hours, 14 hours. The supply line that connects a Hohmann minimum to Mars every 26 months grows into a logistics challenge, so severe that the very concept of supply line from Earth begins to dissolve into something that more closely resembles historical memory than operational infrastructure. Out there, at those distances, the political opinions of Earth become something more than irrelevant. They become, in the most literal physical sense, inaudible. A civilization living at Jupiter's distance from the Sun is a civilization that cannot receive instructions from Earth in time to follow them, cannot call for help in time to receive it, cannot be threatened with consequences in time be deterred by them, and cannot be reached by force in any time scale that corresponds to the events that might provoke sending that force. What develops in those conditions, what must develop, because the physics leave no alternative, is something that the political philosophers of Earth have never been required to fully imagine. Not independence from Earth, but the complete irrelevance of the question of independence, because a relationship that would need to exist for dependence to be meaningful cannot survive the distances involved. The outer solar system is not simply far. It is where the light-year logic begins to make itself felt at the scale of human institutions, rather than merely at the scale of telescopes and theoretical physics. It is where human civilization, if it gets there, will encounter for the first time the experience that every stellar civilization in the universe must navigate if it expands beyond a single system. The experience of being so far from the seat of authority that authority itself becomes a philosophical concept rather than an operational reality. What humanity will build out there, in the cold and the silence and the absolute darkness between the sun and the nearest star, will not be a colony. It will be something that language has not yet developed adequate vocabulary to describe, because the thing itself has not yet existed. It will be built by people who are the grandchildren of people who were born on Mars, who were themselves the grandchildren of people who left Earth, who are the inheritors of a tradition of decision-making under impossible communication delays that stretches back through the Martian frontier and the lunar resource wars to the first moment a satellite was blinded in orbit above this planet, and no one could prove who did it. And the first war fought in those distances. The first conflict initiated among human beings for whom Earth is not a home or an authority, but a dim point of light indistinguishable from the surrounding stars, will begin the way every conflict in this story has begun and will begin, quietly, with a technical malfunction that nobody can quite prove was intentional, with a press release, with paperwork, at a distance where even the paperwork takes hours to arrive. The Asteroid Belt is not what the movies made it. This is worth stating plainly before anything else, because a visual grammar of decades of science fiction has installed in the human imagination an image of the belt as a crowded, chaotic gauntlet, a region of space so densely packed with tumbling rocks that a spacecraft threading through it must dodge and weave continuously to avoid collision, like a pinball navigating a field of obstacles set impossibly close together. That image is wrong in a way that is not merely technically inaccurate, but that inverts the actual strategic reality of the belt so completely that correcting it changes the entire character of what the belt represents as a military and civilizational resource. The asteroid belt occupies an annular volume of space between roughly 2.2 and 3.2 astronomical units from the Sun, a band that contained, by current estimates, somewhere between 1 and 2 million objects larger than 1 kilometer in diameter, an uncounted population of smaller bodies, extending down to gravel and dust that collectively represent a mass approximately 4% of the moon's. These numbers sound large until you distribute them across the actual volume they inhabit. The belt is not a narrow ring. It is a vast three-dimensional torus of space whose inner and outer edges are separated by roughly 225 million kilometers, whose vertical extent spans tens of millions of kilometers above and below the ecliptic plane. The average distance between kilometer-scale objects in the asteroid belt is approximately 1 million kilometers. If you place a spacecraft in the belt and flew it in a straight line, you could travel for years without passing within visual range of any object large enough to see with the naked eye. The belt is, in the experiential sense, almost empty. A spacecraft transiting, it does not navigate obstacles. It navigates a void that happens to contain, at vast and irregular intervals, objects whose existence would only be apparent through instruments. This is not a correction of a minor detail. It is a revelation that the asteroid belt's significance as a strategic resource lies not in its density, but in its composition, its distribution, and extraordinary physics of what it means to have access to essentially unlimited quantities of iron, nickel, cobalt, platinum group metals, and silicates in a gravitational environment so shallow that moving material off these objects requires almost no energy by the standards of anything that has climbed out of planetary gravity well. The largest asteroid, Ceres, has a surface gravity approximately 200 of Earth's. The gravity of a 1-kilometer asteroid is so faint that a human being standing on its surface could achieve escape velocity by jumping. Not by jumping particularly hard, but by jumping at all, with enough care not to angle too steeply and drift away into a slow, unrecoverable heliocentric orbit. Thus vanishing the low gravity is, from a manufacturing standpoint, the single most transformative property the belt possesses. Material on an asteroid surface can be launched into heliocentric space with a velocity increment so small that the energetic cost of doing so is trivial compared to what it costs to launch the same material from the surface of the Moon, from Mars, or from any object large enough that its gravity constitutes a genuine barrier to departure. What this means for a civilization with even modest industrial capability in the belt is that the belt is not merely a source of raw materials. It is a source of raw materials that can be launched into space for essentially zero energy cost at the planetary scale. And material launched into space in a specific direction at a specific velocity follows a trajectory governed by Newtonian mechanics and Keplerian orbital dynamics with a precision and predictability that, once the initial impulse has been applied, requires no further energy input and no guidance. It goes where the math says it will go. It arrives where the math says it will arrive. It arrives moving at a velocity that the math calculated when the impulse was first applied, which may be years or decades before the arrival, and which is determined not by the energy put into the launch, but by the geometry of the orbital transfer, by the depth of the sun's gravity well, and the difference in orbital energy between the departure point and the destination. A 1 kilogram iron fragment launched from a belt asteroid into a transfer orbit toward Earth arrives at Earth-crossing velocity, moving at roughly 11 to 15 kilometers per second relative to Earth's surface, depending on the geometry of the specific transfer. The kinetic energy delivered is not a function of the propulsion system that launched it. It is a function of gravity. The sun did the work. The launch system merely redirected material that the sun then accelerated for months or years, gratis, using the same potential energy well that drives every orbit in the system. An industrial colony in the asteroid belt that wished to deliver kinetic energy to the inner planets would not need a sophisticated weapons program. It would need mining equipment, a mass driver or launch rail capable of imparting a small velocity increment to a prepared projectile, and patience. The patience of orbital mechanics, the willingness to wait 6 months, a year, 2 years for the trajectory to complete itself, is the only rate-limiting factor. The energy is free. The precision is determined by the accuracy of the initial impulse and the quality of the orbital calculation, both of which are engineering problems of a character that humanity has been solving since the first interplanetary probes. This is the physics of an asteroid belt weapons foundry, and it is important to understand that the word foundry here is not metaphorical. The belt contains the raw materials: iron, nickel, carbon, water ice in the outer belt, silicates throughout, from which every component of a kinetic strike system can be manufactured in situ. The projectiles themselves require no exotic materials. Dense, cohesive iron nickel is precisely what many M-type asteroids consist of, and it is available in quantities that make the concept of running out of ammunition essentially meaningless on any time scale shorter than geological. A colony with asteroid mining capability and a functioning mass driver has a kinetic strike capacity that scales with its industrial output, not with its weapons budget, and that can be directed toward targets in the inner solar system with a delivery delay measured in months to years, during which the projectile travels passively with no propulsion system to detect, no thermal signature to track, and no radio emissions to intercept. The detection problem this poses for any inter-system civilization is severe and in some respects fundamental. A kinetic impactor launched from the belt toward Earth or Mars is a dark, cold, inert object moving through space on a trajectory that is indistinguishable at the moment of launch from a background population of natural asteroids in heliocentric orbits. Space surveillance systems designed to track threatening near-Earth objects are optimized for detection at relatively close range, within the orbit of Mars at most, and typically much closer. An object in the belt moving on a transfer orbit that will not reach Earth-crossing distance for 18 months is not, in the current architecture of any nation's planetary defense capability, a routinely monitored threat. The population of belt objects on Earth-crossing trajectories is enormous and incompletely cataloged. Distinguishing an artificial impactor from a natural one requires either extremely precise tracking over a long observation arc, which requires knowing to look at the specific object in the first place, or visual inspection close enough to resolve the object's geometry, which requires a spacecraft and significant lead time. An adversary that controls a belt colony and is willing to exercise patience has, in this physics, an instrument of coercive power that has no clean analog in the history of terrestrial strategy. It is not a weapon that fires and delivers its effect immediately, like a rifle or a missile. It is a weapon whose trigger is pulled months or years before the effect is felt, during which time the triggering event may be entirely undetected, and during which the trajectory, once established, is as immutable as any other orbit in the solar system. You cannot shoot it down with conventional missile defense systems because it approaches from the ecliptic, not from a missile trajectory, and it announces itself only when it has already crossed the detection threshold of the systems watching for it. You cannot negotiate with it, because there is nothing to negotiate with. It is an inert rod of iron following a path that was determined by a decision made a year and a half ago by people who may no longer be in communication with anyone you can reach. The only defenses against this capability are those that address the launch rather than the projectile in flight, and addressing the launch requires either physical presence in the belt, the ability to inspect and interdict a colony's industrial activities at the source, or the development of a belt-based surveillance capability capable of distinguishing artificial launches from a continuous low level of natural ejecta that belt objects produce through micro-impacts and solar wind effects. Neither of these is technically impossible, but both require sustained investment in deep space capability that exceeds what any nation or entity is currently planning, and both raise exactly the kind of question about authority, jurisdiction, and the right to inspect another party's industrial operations in space that the current vacuum of space law is entirely unprepared to answer. And the law is not merely silent on these questions. It is absent. The 1967 Outer Space Treaty prohibits the placement of weapons of mass destruction in orbit or on celestial bodies. It says nothing about placing a mass driver on an asteroid. It says nothing about the rights of a belt colony to conduct industrial operations that have the incidental capability, as a necessary consequence of the physics of launching material from low-gravity bodies, to double as a kinetic bombardment system against any inter-system target. The distinction between a mining operation and a weapons program in the asteroid belt is not a legal distinction or a political one. It is an intention that exists in the minds of the people operating the facility, and that cannot be verified from a distance, and that the physics do not encode into trajectories themselves. An iron rod launched toward Earth on a commerce trajectory and an iron rod launched toward Earth on a strike trajectory are identical objects following nearly identical paths until final moments of approach, when modest terminal guidance adjustment, or simply the absence of a course correction that would have been applied if the intent were commercial, determines which one it turns out to have been. These are not hypothetical scenarios. They are the predictable consequences of the physics of low-gravity industrial operations in the outer belt, applied to the geopolitical logic that this documentary has been tracing from the orbital commons above Earth's atmosphere outward through the cislunar resource competition and the Martian frontier. The logic does not change as the distances grow. It intensifies because the distances that insulate a belt colony from retribution are so much greater than those separating Earth from Mars that the cost-exchange ratio of military projection into the belt makes the economics of projecting force to Mars look straightforward by comparison. But the asteroid belt is not the outermost theater of this logic. It is a way station, the real architecture of the outer solar system, the framework of gravitational geometry that will eventually define where power is projected and where it is irreducibly concentrated, is organized not around the rocky bodies themselves, but around the points in space where gravity and orbital mechanics conspire to create stable positions that require almost no energy to maintain, and that command, with a geometric completeness that the word fortress barely captures, the trajectories of everything moving through the inner and outer solar system alike. These are the Lagrange points. Joseph Louis Lagrange, working in the 18th century on the mathematics of the three-body problem, the motion of three gravitationally interacting objects, a problem that has no general closed-form solution, but that admits to specific special cases, identified 5 positions in a two-body gravitational system where a small third object could maintain a fixed position relative to the 2 larger ones without any propulsion. These positions are not arbitrary geometric constructions. They are solutions to equations of motion that the universe enforces without exception. An object placed at a Lagrange point and given the correct initial velocity will remain there, or in a bounded orbit around that point, indefinitely, held by the balance of gravitational and centrifugal forces without any need to fire an engine, expend propellant, or maintain any form of active station, keeping beyond the occasional small correction needed to account for gravitational perturbations from other bodies in the system. The first three Lagrange points, L1, L2, and L3, lie on the line connecting the two primary bodies. L1 sits between them, at the point where their gravitational attractions cancel. L2 lies behind the smaller body, on the far side from the larger. L3 sits on the opposite side of the larger body, directly across the system. All three are what mathematicians call unstable equilibria, points where a small perturbation will cause an object to drift away rather than return. The way a ball balanced on the top of a hill will roll away if nudged rather than settle back into position. They are usable as orbital staging positions with modest station keeping, and several real spacecraft occupy the Earth's sun L1 and L2 points today. The Discovery Solar Monitoring Spacecraft at L1, the James Webb Space Telescope in a halo orbit around L2. But their instability means that maintaining a position there has an ongoing energetic cost, and that cost, while small, is non-zero. The fourth and fifth Lagrange points, L4 and L5, are different in a way that matters profoundly for the strategic geometry of the solar system. They sit along the orbit of the smaller body, 60 degrees ahead of it and 60 degrees behind, forming equilateral triangles with the two primary masses. And they are stable equilibria, points where a perturbed object experiences a restoring force that tend to push it back toward the equilibrium, the way a ball at the bottom of a bowl will roll back to center if disturbed. An object placed at an L4 or L5 point does not need active station keeping to remain there. The gravitational geometry of the system holds it, and has held objects there since the solar system formed. We know this because we can observe it. The Trojan asteroid to Jupiter. Two swarms of rocky and carbonaceous bodies, one cluster at the sun Jupiter L4.60 degrees ahead of Jupiter in its orbit, one clustered at L5 60 degrees behind, are objects that have been co-orbiting with Jupiter for billions of years without any propulsion, held by the same gravitational geometry that Lagrange's mathematics predicted. The L4 Trojan swarm alone is estimated to contain more objects than the main asteroid belt. The strategic implications of the Lagrange points emerge from two properties that combine in a way no terrestrial fortress ever has. The first is the cost of maintenance. An installation at a stable L4 or L5 point requires almost no energy to remain in place. The Sun-Earth L4 and L5 points, located 60 degrees ahead of and behind Earth in its orbit, are approximately 150 million kilometers from Earth, the same as Earth's distance from the Sun. The Sun-Jupiter L4 and L5 points are approximately 780 million kilometers from Jupiter. These are immense distances by any terrestrial standard. But the energy required to maintain a position, there is not a function of the distance. It is a function of the gravitational stability of the point, which for L4 and L5 is intrinsic. You do not pay a maintenance cost proportional to how far you are from Earth. You pay almost nothing because the position is gravitationally self-maintaining. The second property is trajectory geometry. Every object in the solar system, every spacecraft, every cargo convoy, every would-be impactor, every vessel traveling between the inner and outer planets follows a trajectory governed by the same orbital mechanics that make the Lagrange point stable. Those mechanics are not secret. They are predictable, reproducible, and shared by anyone with a computational capability to run an orbital propagator. The trajectories that connect Earth to Mars, Earth to the Belt, Earth to Jupiter, the corridors of practical interplanetary transit, are not arbitrary. They are constrained by the geometry of the solar system, by the relative positions and velocities of the planets, by the imperative to minimize propellant expenditure. And many of those corridors pass through, or in close proximity to, the Lagrange points of the major planetary systems. An installation at the Earth-Sun L4 or L5 does not merely sit in those positions. It sits at a position from which a significant fraction of the trajectories used to reach the asteroid belt and the outer planets are geometrically accessible, not in the sense of being physically adjacent, but in the sense of being reachable with modest velocity increments that an installation at that location could apply to any object it controlled. The ability to apply a small velocity increment to an object at an L4 or L5 location is the ability to redirect that object onto an enormous variety of trajectories, because at those locations the available delta velocity, even from a low-thrust propulsion system, intersects with the orbital mechanics in ways that make a wide range of destination orbits achievable. This is what strategists mean when they call the Lagrange points high ground. Not high ground in the terrestrial sense of elevation that commands lines of sight, but high ground in the gravitational sense of potential energy that commands lines of transit. The Sun-Jupiter L4 and L5 points, the locations of the actual Trojan asteroid swarms, represent this geometry at its most extreme scale. Jupiter's gravity is so dominant in the outer solar system that the Lagrange geometry of the Sun-Jupiter system organizes, to a significant degree, the orbital dynamics of everything between the asteroid belt and the ice giants. The L4 and L5 points of that system are not merely stable parking orbits. They are positions from which the gravitational topology of the outer solar system is, in a deep orbital mechanical sense, commanded, not because a weapon that would have shorter range, but because the trajectories that objects at those points can reach efficiently, given modest propellant expenditure, encompass the most strategically important volume of the outer solar system, and because an installation at those points can be supplied and maintained at a cost far lower than any equivalent installation elsewhere in the same region. The physics of the strategic high ground are not governed by current technology. They are governed by Lagrange's mathematics and by Kepler's laws, which will not change. The question of who controls the stable Lagrange points of the major sun-planet systems in the outer solar system is not a question of where put a military base in some future scenario. It is the deepest geopolitical question of the outer solar system, and has already been answered in the most important sense. No one controls those points, and no framework of international law currently recognizes them as anything other than unregulated space. They are not territory under the Outer Space Treaty, because the Outer Space Treaty does not address gravitational equilibrium points that have no physical surface, no national boundary, and no administrative existence in any existing legal framework. They are not navigational hazards, because an installation that would not obstruct navigation. They are, in the most precise legal sense, nothing, which is to say, they are available to whoever gets there first with the capability to maintain presence, and they will be extraordinarily expensive to contest once that presence is established. The effort required to dislodge an installation from a stable Lagrange point is not comparable to the effort required to establish one. Establishing requires only the energy to transit there and the materials to build with. Dislodging requires overcoming whatever defensive systems the installation has developed during time it has occupied the position, projecting sufficient force across the distance, separating the attacker from the target, and doing so against an adversary that has chosen its position for precisely its gravitational advantages. This asymmetry between establishment and contestation is a defining strategic property of the Lagrange points, and it means that the race to establish a meaningful presence at the most strategically significant of these positions is not a race that can be won after someone else has already won it. It can only be won before. The window for that race is open now and narrowing. Beyond the belt, beyond the Trojan clouds, the solar system makes a transition that human language has never been required to fully characterize. The gas giants are not large planets. They are a different category of object entirely. Worlds whose physical scale so exceeds the familiar that the comparison to Earth or Mars functions more as a gesture toward the idea than as an accurate impression of the reality. Jupiter is the largest planet in the solar system by mass, possessing more than twice the mass of all other planets combined. Its equatorial diameter is approximately 11 times Earth's. Its volume could contain over 1,300 Earths. Its magnetic field is roughly 20,000 times stronger than Earth's, extending in a magnetosphere that dwarfs the planet itself, a bubble of electromagnetic influence that stretches 5 million kilometers toward the Sun and extends in the opposite direction past the orbit of Saturn. Within this magnetosphere, the radiation environment is among the most severe in the solar system. The innermost regions, where Jupiter's magnetic field funnels charged particles into a belt analogous to Earth's Van Allen belts, but incomparably more intense, deliver radiation doses that would kill an unprotected human being in minutes. Even the hardened electronics of robotic probes, specifically designed and tested to survive space radiation, have been damaged and destroyed by prolonged exposure to Jupiter's radiation environment. The Galileo spacecraft, which orbited Jupiter for 8 years before being deliberately deorbited into the planet's atmosphere in 2003, survived only because its orbit was carefully designed to minimize time spent in the most intense radiation zones. This radiation environment is not merely a hazard for human habitation near Jupiter. It is a defining feature of the military and industrial geography of the Jovian system, in the same way that mountain terrain, river systems, and coastal geography define the military and industrial geography of terrestrial regions. It concentrates human activity and infrastructure in the portions of the Jovian system that are survivable, primarily the outer moons, where the radiation fluxes fall into levels that can be managed with shielding and where the gravitational and magnetic environment provides resources and energy sources that no other location in the outer solar system can match. The innermost of Jupiter's 4 large Galilean moons is Io, and Io is unlike any other solid body in the solar system in a way that simultaneously makes it extraordinarily valuable and extraordinarily dangerous. Io is the most volcanically active world known to science. Its surface is a continuously resurfaced landscape of lava lakes, volcanic calderas, sulfur plains, and plume deposits that change on timescales of weeks to months. There is no impact crater terrain on Io, because the resurfacing rate from volcanic activity buries craters faster than impacts can create them. The energy source for this volcanism is not radioactive decay in the interior, as is the case for Earth's geological activity, but tidal flexing, the continuous kneading of Io's interior by the competing gravitational influences of Jupiter, Europa, and Ganymede, which conspire in a gravitational resonance that maintains Io's orbit at a modest but permanent eccentricity, forcing the moon to flex rhythmically as it orbits, converting gravitational potential energy into heat in the interior with a power output that exceeds Earth's total internal heat production by more than an order of magnitude. For a civilization with the capability to operate in the radiation environment of Io's orbit, and that is a significant qualification, because the radiation flux at Io's distance from Jupiter is severe enough that any long-duration human presence there would require either extraordinary shielding or robotic operation with periodic human crew rotations in heavily shielded habitats. Io's continuous volcanic activity represents an industrial energy source of essentially unlimited scale. The heat flux from the interior is vast and self-renewing. The surface chemistry provides sulfur dioxide, silicates, and the raw material for a range of industrial chemical processes. The orbital position within Jupiter's powerful magnetic field provides something even more extraordinary: the potential to extract electrical power from the electromagnetic interaction between a conductor moving through that field and the field itself, using Io's motion through Jupiter's magnetosphere as the driving force for magnetohydrodynamic power generation. The physics of this energy extraction are real and have been demonstrated. The Galileo spacecraft actually observed natural Alfvén wing currents flowing along Io's flux tube, confirming that the electromagnetic coupling between Io and Jupiter's magnetosphere carries electrical currents of enormous scale. Whether this can be practically exploited for industrial power is an engineering question. The physical basis for the energy source is not speculative, but Io's radiation environment makes it as a location for sustained human industrial activity, something close to a definition of inhospitality. The surface of Io lies within the most intense radiation belts of the Jovian system. Unshielded biological tissue at the surface would accumulate lethal radiation doses in minutes. Electronics without heavy shielding would fail rapidly. Any industrial operation on Io would need to be conducted either robotically or by crews spending the minimum possible time on the surface, returning to heavily shielded orbital or surface habitats for rest and recovery. This is not an insurmountable engineering challenge. Humanity has operated equipment in high radiation environments before, from nuclear power plants to research facilities. But it defines Io as a place where the energy cost of human presence is not measured in propellant, but in biological tolerance and engineering complexity, and where the military geography is defined by the radiation itself as much as by the topography, a faction that controls Io's industrial capacity. that can sustain robotic or semi-automated mining and processing operations in the radiation environment, exploiting the volcanic heat and the electromagnetic energy of Jupiter's magnetosphere. Controls a manufacturing base that has no equivalent in the inner solar system for sheer resource density and energy availability. But that control is meaningless unless it can be defended, and defending a facility on Io means defending it in an environment where the attacking force faces the same radiation exposure as the defending force, where the terrain is continuously reshaped by volcanic activity that neither side controls, and where the proximity to Jupiter's gravitational and magnetic influence imposes constraints on orbital access that have no terrestrial parallel. If Io is an industrial engine of the Jovian system, what lies one moon further out is something else entirely, something that may represent the most consequential strategic objective in the outer solar system, measured not by industrial output or gravitational advantage, but by what it contains and what that containment means for the long-term survival of human civilization beyond the inner planets. Europa is smaller than Earth's moon. Its surface is a landscape of cracked and refrozen ice, crossed by systems of ridges and dark lineaments that trace the stress patterns of crust in constant motion. Not the geological motion of plate tectonics, but the tidal flexing that also drives Io's volcanism, applied here to an ice shell rather than a silicate interior. The ice surface of Europa is geologically young by solar system standards, perhaps 10 to 30 million years old in its current configuration, which implies that it is being continuously resurfaced by material from below. Below the ice, held liquid by the same tidal heating that resurfaces it from above, is an ocean. The existence of Europa's subsurface ocean is not a hypothesis. It is established by multiple independent lines of evidence. The magnetic field measurements taken by the Galileo spacecraft, which detected an induced magnetic field consistent with conducting saline fluid in Europa's interior. The geological evidence of the surface ice behavior, including features that require liquid water beneath to explain their formation. The gravity data consistent with a differentiated interior, and the detection by the Hubble Space Telescope and later instruments of water vapor plumes venting from the surface, which implies subsurface liquid water under sufficient pressure to reach escape from the ice shell and vent into space. The ocean beneath Europa's ice is estimated to contain more liquid water than all of Earth's oceans combined. It has been in contact with the rocky seafloor below it for billions of years, warmed from below by tidal heating, and potentially from hydrothermal vents analogous to those on Earth's ocean floors. The strategic value of this ocean is not primarily biological, although the question of whether it harbors life is one of the most important scientific questions in the solar system, and will be at the center of every political argument about what Europa is to be used for. The strategic value is physical. Water, liquid water, already in the liquid state, in quantities that dwarf any reservoir anywhere else in the outer solar system accessible without drilling through tens of kilometers of ice. Water that can be electrolyzed into hydrogen and oxygen propellant. Water that can be used for radiation shielding, for agricultural systems, for industrial chemistry, for the biological requirements of a large population. Europa's ocean is not merely a scientific curiosity or a potential cradle of alien life. It is, at the distances of the outer solar system, the single most valuable non-stellar resource within reach of any civilization trying to establish a permanent presence beyond the asteroid belt. Any conflict over Europa would be a conflict over access to that ocean, which means a conflict conducted partially on the ice surface, in the radiation environment of Jupiter's outer magnetosphere, and partially beneath the ice, in the absolute darkness of a sealed ocean that has never seen sunlight, and that is accessible only through drill holes or melt through vehicles that must penetrate 10 to 30 kilometers of ice before reaching the water below. The tactical geometry of a conflict beneath Europa's ice is unlike any military environment that has ever existed in human history. The acoustic properties of liquid water make sonar the primary detection method. The darkness is total. Navigation depends entirely on dead reckoning and sonar mapping. The sealed environment, a global ocean enclosed by an ice roof that is tens of kilometers thick and a rocky floor whose exact topology is unknown, is smaller than Earth's oceans in horizontal extent, but comparable in depth, and it is entirely enclosed, with no surface, no sky, no possibility of aerial support, no possibility of orbital observation through the ice. A battle fought in Europa's ocean will be the most claustrophobic military environment conceivable. A dark, cold, pressurized maze navigated by acoustic instruments in an enclosed global space that is simultaneously the most precious resource in the outer solar system and the most inaccessible military theater in the history of human conflict. The civilization that establishes a functioning access point to Europa's ocean, a drill station through the ice that provides regular, reliable access to the liquid water below, holds something that cannot be replicated elsewhere within practical reach of the outer solar system's human population. It holds the ability to provision fleets, to supply habitats, to sustain populations at a scale that the ice mining operations of the belt cannot match for sheer volumetric availability. In a civilization spread across the outer solar system, where water is the fundamental currency of survival and the limiting factor on everything from rocket propellant to agricultural output, control of Europa's ocean is the kind of structural advantage that does not merely provide a competitive edge. It provides a resource foundation from which dominance over the entire Jovian system becomes achievable, and from which the leverage of resource denial over any party that depends on Jovian system water becomes a permanent coercive tool. The political and military implications of this have not been formalized in any existing framework of international law, because the existing frameworks were not designed for a solar system in which any of this is imminent. The Moon Agreement of 1979, which would have established the Moon and, by extension, other celestial bodies as the common heritage of mankind, requiring international governance of their resource exploitation, was never ratified by any major spacefaring nation. The Outer Space Treaty says nothing that bears specifically on the question of who may drill through Europa's ice to access the ocean below, or what authority governs the conduct of entities that do so, or whether another party may prevent them from doing so by force if it judges the consequences of their access to be inimical to its interests. That question, who may access Europa's ocean, under what authority, governed by what rules, enforced by what mechanism, is a question that will eventually need an answer, and that the existing legal architecture of human civilization has not provided. The absence of that answer is not, in the context of the history this documentary has been tracing, a surprising condition. It is a predictable state of affairs when the stakes become real faster than the institutions designed to manage them can adapt. The light from the sun reaches Jupiter in approximately 43 minutes on average, 33 minutes at closest approach, 52 minutes at greatest separation, depending on where the two bodies are in their orbits. A radio signal, traveling at light speed, crosses the same distance in the same time. At the Jovian system, the one-way communication delay from Earth is between 33 and 52 minutes, a round-trip delay of between 66 minutes and 104 minutes. In a tactical military engagement that unfolds over minutes, this delay is not an inconvenience. It is not a limitation on response time. It is a mathematical proof that Earth has no role in the engagement whatsoever, in any operational sense. That by the time the first report of a conflict in the Jovian system reaches Earth, the conflict will have progressed by an hour, and by the time any response from Earth could be transmitted back, the conflict will be 2 hours further along. A battle that begins and ends in 90 minutes, which is not an unreasonable estimate for a sharp, decisive engagement between forces that have already closed the weapon's range, will be over before Earth receives a signal that has begun. This is not merely a command and control problem of the kind that military organizations have always managed by delegating authority to field commanders. It is a mathematical end of a particular kind of relationship between Earth and the human civilization that exists beyond it. On the Moon, Earth's authority is attenuated by a 1.3-second delay, present but practically relevant for crisis management. On Mars, it is made operationally impossible by a 10 to 22-minute one-way delay. At the Belt, the delay ranges from 3 minutes to 15 minutes, depending on orbital position. Significant but not absolute. At Jupiter, it is so large and so invariant regardless of the technology used to transmit, that it does not merely complicate the exercise of authority. It terminates it. A government on Earth that claims sovereignty over a Jovian colony, that asserts the right to govern it, tax it, direct its policies, restrict its activities, and compel its compliance, is asserting a form of sovereignty that cannot be exercised in any operational sense at the timescales that matter. It can send ships, but those ships will take years to arrive. It can send commands, but those commands will arrive more than an hour after they were sent, and the response will take another hour to return. It can pass laws, but it cannot enforce them. It can claim authority, but it cannot demonstrate it in any circumstance that tests the claim. The colony, if it chooses not to comply, has the same defense that the Martian colony has, plus the addition of distance so vast that the cost of military projection is not merely high, but, at the present and near future state of human technology, essentially prohibitive for any sustained campaign. The light hour problem at Jupiter is not a version of the 26-minute problem at Mars. It is a qualitative transformation of the same principle, taken to a point where the phrase Earth's authority loses whatever residual operational meaning it retained at Martian distances and becomes purely nominal, a designation with no mechanism of enforcement, no capacity for a real-time response, and no practical meaning to the people. It nominally governs beyond whatever psychological or sentimental weight the words Earth and home and origin carry for a population that may have been born in the radiation-shielded tunnels of a Jovian moon and has never seen the blue planet, except in photographs. What emerges at Jovian distances is not simply a distant colony with de facto autonomy. It is a civilization with no structural connection to Earth's political arrangements beyond the historical accident of shared biological origin. The institutions, the laws, the economics, the security arrangements, the governance frameworks that organize human life on and near Earth, all of them were designed for a species confined to a single world, or at most to a region within a few light minutes of that world. At Jovian distances, they are not merely inadequate. They are irrelevant in the way that the laws of medieval England are irrelevant to the daily life of a person living in the 21st century, still present in the historical record, still occasionally cited in legal arguments about the origins of specific doctrines, but not governing anything that actually happens. The civilization that develops in the Jovian system will develop its own governance, its own laws, its own military arrangements, and its own strategic interests, which may or may not align with those of the inner solar system, and which will be enforced by whatever local power structures emerge from the specific geography of the Jovian moons, the radiation belts, the Lagrange points of the Sun-Jupiter system, and the industrial capacity that Europa's ocean and Io's volcanism and the Trojan asteroids provide. It will not be governed from Earth. It cannot be. The physics say no, with a finality that admits no negotiation. And if this is true at Jupiter, at distances where the light travel time is measured in tens of minutes, where a round trip is still achievable in hours, then what is true at Saturn, at Uranus, at Neptune, at the scattered disk, and the Kuiper belt, and the inner edge of the Oort cloud, where the light travel time to Earth is measured not in minutes, but in hours, where the round trip is measured in days? At those distances, the concept of relationship with Earth, political, economic, or military, does not merely break down under strain of communication delay. It becomes, in the most literal physical sense, a different order of thing from any relationship that has ever existed between human communities. The delay is no longer a technical problem to be worked around by wise delegation and robust local governance. It is a wall made of light seconds and then light minutes and then light hours that separates, with increasing completeness, those who live beyond it from those who do not. The solar system is large. This sentence has been said many times and understood very rarely, because human intuition evolved in the context of scales measured in meters and kilometers and perhaps thousands of kilometers, does not naturally extend to the distances that separate the planets. But what this documentary has been tracing, from the orbital commons above Earth to the gravitational equilibria of the Jovian Trojans, is a story that the solar system size makes not merely possible, but inevitable. A story about what happens when the distances between human communities grow large enough that the assumptions underpinning every form of governance, every form of military deterrence, and every form of political authority that human civilization has ever developed simply cease to apply. The first space war will not be the last. The first will establish patterns, legal, military, technological, psychological, that will shape every subsequent conflict for as long as human beings exist in space. And the stakes of those patterns, of the precedent set in the first orbital engagement, the first lunar resource dispute, the first Martian independence crisis, the first kinetic strike launched from the belt, and the first battle fought in the darkness beneath the Jovian moon's ice, are not merely the stakes of the people involved in those specific conflicts. They are the stakes of every human being who will ever live beyond this planet. Every generation yet unborn that will inherit either a solar system organized by legal frameworks, norms, and institutions capable of managing the pressures that distance and resource scarcity and civilizational divergence create, or a solar system organized by the outcomes of conflicts that were never governed by anything except the physics of kinetic energy, the patience of orbital mechanics, and the willingness of whoever was most ruthless to apply them. We are, right now, in the period before the patterns are set, in the period when the laws could still be written, the norms could still be established, the frameworks could still be built that might make the next century of human expansion into the solar system something other than the recapitulation, at interplanetary scale, of every territorial war and resource conflict and colonial suppression that the surface of this planet has ever hosted. That window is not indefinitely open. It closes as the capabilities develop and the interests solidify and the positions harden, and the first irreversible act is committed by someone who calculated that the absence of framework to prevent it was, in practice, an invitation. The question that this journey has been building toward, through the jammed satellites and the blinded reconnaissance assets and the contested lunar water and the silent Martian battlefields and the gravity-assisted impactors of the belt and the light-hour isolation of the Jovian system, is not merely where the first space war will begin. It is whether the species that evolved on this particular blue world, in this particular solar system, at this particular moment in cosmic time, is capable of recognizing the full shape of what it is building, at the scale at which it is building it, in time make choices that its descendants will not have reason to regret, because the outer solar system does not merely represent the end of Earth's authority over human affairs. It represents the beginning of something that this civilization has never faced before, the management of its own existence not as a species confined to a single world or a single star system, but as a civilization distributed across volumes of space large enough that no single authority, no single government, no single set of values or laws or military doctrines can span the distance without being transformed beyond recognition by the time it arrives. The question of how to remain, in any meaningful sense, a single civilization, or whether to try, or whether the attempt itself is the source of the violence rather than the solution to it, is a question that the physics of the solar system is now beginning, slowly and with the patience of orbits, to force upon us. The answer to that question will not be found in the orbital commons above Earth, where the first satellites are already watching each other with instruments whose purpose requires no declaration. It will not be found on the moon, where the permanently shadowed craters wait in their 2 billion year silence for the first claim that cannot be diplomatically resolved. It will not be found on Mars, where the 26-month window ticks and the communication delay grows, and the first generation of children born under a rust-colored sky begins to understand that their relationship to Earth is something different from what their parents believed it was. It will not be found in the belt, where the mass drivers wait in the low gravity of iron-nickel asteroids, or the Lagrange points where the gravitational geometry of the solar system offers its most strategically complete positions to whoever arrives first and understands what they are standing in. It will be found, if it is found at all, in the choices made now, in this brief and unrepeatable interval of human history, when the capabilities and the stakes have grown large enough to make the question urgent, but when the patterns are not yet fixed and the first irreversible acts have not yet been committed, and the window through which a different kind of future might still be threaded remains. If narrowly open, what we do with that window is not a question of science or physics or military strategy, though it requires all of these to understand it properly. It is a question of what this species, in the full knowledge of its own history, and the full understanding of the physics of the environment it is moving into, decides to be, what kind of civilization it chooses to carry with it into the cold and the dark and the silence beyond this world. The stars are watching, in the only way that stars can watch, with the indifferent patience of nuclear fires that have been burning for billions of years and will burn for billions more, and that have no opinion about what the small, warm, briefly luminous creatures on the third planet of this particular G-type star decide to do with the few centuries they have before the decisions become irreversible. But we have opinions. We have choices. We have, in this moment, the knowledge of what is coming and the still remaining possibility of shaping it. That knowledge is not comfortable. It was never meant to be. It is the kind of knowledge that the universe gives only to creatures capable of using it, and only when a time has come that not using it is no longer an option. The first space war will begin. The physics say so. The history says so. The logic of resources and distance and authority and the irreducible human tendency to contest what is valuable and fight over what cannot be shared without agreement. All of it says so. The only questions that remain are questions of form, of timing, of scale, and what we choose to build in the time between now and then that might, if we are fortunate and wise in equal and sufficient measure, determine how it ends. And there is something that the strategists who model these conflicts rarely pause long enough to name, something that lives not in the equations of orbital mechanics or the calculus of kinetic energy, but in the deeper logic of what a war in space would leave behind. Not the politics, not the territorial settlements or the resource agreements negotiated in whatever passes for a peace conference between parties separated by 100 million kilometers. What it leaves in the physical environment itself, in the solar system as a place, in the dark, patient, indifferent medium through which every future ship, every future colony, every future generation of human beings will have to navigate for as long as the civilization continues to exist. Think again about Kessler's insight, but do not confine it to the orbital bands above Earth. Think of it as a principle, as a statement about what happens when any environment becomes sufficiently populated with human debris and human violence to turn against the very species that created the conditions for its own denial. In low Earth orbit, the threshold of the cascade is measured in object density at a specific altitude band, a number that current models suggest may already have been approached in certain regions of the shell between 600 and 1,000 kilometers above the surface. The cascade, if it begins, will close those altitudes to operational spacecraft for centuries. A century is a long time in human terms. In cosmic terms, it is almost nothing, a flicker, a brief interruption, a transitional period before some future civilization develops the technology to clean the debris field and reclaim the orbital environment for whatever they intend to do with it. The damage is severe. It is not permanent. But now extend the principle outward. Carry it to the asteroid belt. Carry it to the space around Jupiter's moons, to the Lagrange points of the outer solar system, to the deep interplanetary corridors through which every Hohmann transfer must pass. In those environments, the question is not whether a Kessler cascade is achievable. The object density in the belt and the outer system is far too low for spontaneous cascades of the kind that threaten low Earth orbit. The question is what an adversary willing to deny resources might do to an economic zone, deliberately, as an act of war, using the same physics, but on a different scale and with a different timescale of consequence. Imagine a faction, a government, a corporation, an ideological movement of sufficient technical sophistication that controls mining operations in the asteroid belt and determines, in the course of a conflict, that it cannot hold those operations against an advancing force. It does not need to destroy its own infrastructure. It does not need to fight a pitched battle it cannot win. It needs only to accelerate, in carefully calculated directions, the mass that it has already processed. Thousands of tons of refined iron and nickel and carbonaceous material, launched on trajectories calibrated not to reach any specific target, but to populate specific regions of heliocentric space with dense, slow-moving clouds of debris at orbital velocities that no spacecraft can safely transit. The Hohmann transfer corridors between Earth and the belt, the approach paths to the most productive mining regions. the gravitational shallows around the Lagrange points, where any future installation would need to station its resupply ships. These are not weapons pointed at a specific target. They are weapons pointed at the environment itself, designed not to destroy an adversary's current assets, but to deny access to an entire economic zone of the solar system for decades or centuries, to render the most productive industrial regions inaccessible not to this generation competitors, but to every generation that follows. The winner of such a campaign does not inherit the riches of the asteroid belt. The winner inherits a locked cage, its most valuable contents unreachable behind a debris field that no current technology can clear in any economically rational timescale, surrounded by approach corridors that any responsible mission planner would route around for the next 200 years. This is the ultimate expression of the scorched earth strategy applied to space. Not burning the fields, because there are no fields, but salting the orbits. And the particular horror of it is that the economics are favorable to the party willing to do it. Moving mass in the belt is cheap. The energy required to redirect a processed asteroid fragment into a debris-generating orbit is trivial compared to the energy required to mine it in the first place. The cost asymmetry between creating a debris hazard and clearing one is so severe that it represents perhaps the most cost-effective denial of access strategy available in any military environment humanity has ever operated in. A conflict that reaches this stage does not merely end in a draw. It ends in the deliberate impoverishment of all future humanity, the closing of an economic frontier by the combatants who could not win it and therefore ensure that no one would. And yet, even this is not the most lasting consequence. Even the centuries-long closure of the belt's most productive regions is, in the cosmic timescale, a temporary condition. Materials disperse over time. Orbit evolve under the slow influence of radiation pressure and gravitational perturbations. A debris field that closes a transfer corridor in the year 2200 will not close it forever, given enough time, and the solar system has more time than human imagination can comfortably process. The debris will thin, the orbits will shift, and whatever civilization exists in the 35th century will find those corridors accessible again, perhaps not knowing why they were empty for so long, or what was lost in the conflict that emptied them. But there is a category of weapon that does not thin. There is a category of consequence that the solar system's patient orbital mechanics will not resolve on any time scale that the civilization needs to plan for. They have no name in common usage because they have never existed before. Call them the weapons that outlive their makers. Kinetic impactors, inert masses of dense metal, accelerated interplanetary velocities in the vacuum of space, moving along trajectories calculated before the wars that produced them ended and the civilizations that launched them collapsed or transformed beyond recognition. In the vacuum of space, there is no friction. There is no air resistance. There is no weathering, no corrosion, no degradation of any kind in the most fundamental sense. A metal object moving through the interplanetary medium is not a metal object aging. It is a metal object traveling. It will continue to travel at the same velocity, in the same direction, until it encounters another mass large enough to significantly alter its momentum. In the absence of such an encounter, it will travel that trajectory for millions of years. Consider what this means for a conflict fought in the outer solar system, in the belt, around the Jovian moons, in the deep interplanetary space between any two worlds. Every kinetic impactor accelerated toward a target and then missed. Every iron slug or processed asteroid fragment that was aimed at an enemy depot or enemy ship and struck empty space instead does not stop. It continues. It follows its trajectory outward through the solar system or inward toward the sun, or on a hyperbolic path that will eventually carry it out of the solar system entirely, or on an elliptical orbit that will bring it back to the inner solar system periodically, on timescales of decades or centuries or millions of years, until it strikes something. Every automated weapons platform launched into deep space during a conflict and then lost, damaged, its controllers dead, its target destroyed, its mission purpose dissolved by the peace or the armistice, or simply collapse of whoever sent it, continues to exist in that orbit, continues to carry whatever kinetic and explosive capacity it was given, continues to represent a hazard to any spacecraft that crosses its path, with no ability to communicate, no way to distinguish friend from enemy, no mechanism for receiving a stand-down order that its creators are no longer alive to transmit. The solar system is large, a weapons platform lost in the outer belt, in the deep space beyond Jupiter, in the scattered disk at the edge of the planetary region. Such an object could drift for centuries before its orbit intersects anything of significance. During those centuries, civilizations will rise and fall and transform. The conflict that produced the platform will become history, then archaeology, then legend, then the kind of deep background context that no one actively thinks about. And then the platform will pass through a volume of space that has become economically important, and its ancient targeting logic will activate, or its propellant will vent catastrophically, or it will simply impact a habitat or a ship or a fuel depot with the speed of a piece of solar system history that has been moving at 3 kilometers per second for 400 years. This is not metaphor. It is applied Newtonian mechanics. An object in motion in a vacuum stays in motion. The weapons that a civilization launches into deep space are the longest-lived artifacts that civilization will ever produce, longer-lived than any monument, any piece of written language, any constructed object on a planetary surface subject to the slow entropy of geology and atmosphere and time. A kinetic impactor launched in the year 2200 during a conflict over a Jovian mining operation will still be moving at approximately the same velocity in the year 5000, in the year 10,000, in the year 100,000, still carrying the kinetic energy of its launch, still following a trajectory that was calculated during a war that no one alive will remember, still representing a lethal hazard to whatever spacecraft or habitat or civilization is unfortunate enough to cross its path. The solar system is not a battlefield that can be cleaned up after conflict ends. It is a medium in which the consequences of conflict persist for durations that dwarf the history of organized human civilization by factors of thousands. Every war fought in space is fought not only against the adversary present, but against every civilization that will ever use that same space afterward. The debris, the weapons platforms, the kinetic impactors, the derelict ships still loaded with propellant and explosive payloads, these are not a cost borne by the combatants. They are a cost deferred indefinitely onto all future inhabitants of the solar system, without their consent, without their knowledge, without any mechanism by which they can redress the negligence or the deliberateness with which their inheritance was compromised. There is a word for a civilization that bequeaths its descendants a permanently degraded environment. There is a word for a species that converts the resources of its home system into weapons whose consequences extend beyond any human purpose they were ever intended to serve. Those words are not comfortable words. They are words that the civilization, which has already filled the orbital shell above its home planet with debris that will outlast its current political arrangements by centuries, is already beginning to deserve. And it is precisely here, at the intersection of these long time scales and these permanent consequences, and this absolute cosmic silence that surrounds the planet where all of this is beginning, that the deepest question this journey can ask begins to take its full shape. The galaxy is approximately 13 billion years old. It contains somewhere between 200 and 400 billion stars. Of those stars, a significant fraction, the precise number is unknown, but current estimates based on Kepler Space Telescope data suggest that virtually every star hosts at least one planet, and that a substantial fraction of those planets orbit in habitable zones where liquid water is possible, represent, in principle, environments capable of supporting the emergence and persistence of complex chemistry. And from complex chemistry, life, and from life, over time, intelligence, and from intelligence, technology, and from technology, the capacity to do exactly what the civilization is beginning to do, reach beyond the world where it began, into the wider system of worlds that its stars arranged around itself. In a galaxy of this age, containing this many stars, with this prevalence of potentially habitable worlds, the question of whether other technological civilizations have arisen before now is not really a question of probability. The probability, Under any reasonable set of assumptions about the rate of life emergence and the likelihood of intelligence developing, it is vanishingly small that the civilization is the first to reach the technological threshold that enables interstellar communication. The scale of the galaxy, the age of the galaxy, the sheer number of opportunities that have existed over billions of years for this process to occur, all of it points toward a universe in which the civilization should expect to find itself surrounded by evidence of others. And instead, it finds silence. Not a partial silence. Not a silence from which signals occasionally emerge when we look carefully enough with sensitive enough instruments in the right parts of the spectrum. A profound, systematic, universal silence that has persisted across every search conducted by every SETI effort mounted since Frank Drake turned a radio telescope toward two nearby stars in 1960 and heard nothing but a background noise of the cosmos that was not, in any detectable way, talking back. The Fermi paradox. The gap between the expectation of a galaxy filled with evidence of technological civilizations and the observation of a galaxy that appears, from this vantage point, to contain none, is one of the most uncomfortable facts in science, not because it proves something specific, but because every explanation it demands is either deeply sobering or deeply troubling, and some of the most plausible explanations are both. Among those explanations, there is a category that bears particular weight in the context of everything this journey has covered. It is a hypothesis of self-destruction, the suggestion that the silence of the cosmos is not empty because civilizations never rise, but because they arise and then, with a regularity that the cosmic statistics must ruthlessly reflect, destroy themselves before they can make any lasting impression on the universe around them. Not destroyed by asteroid impacts or gamma-ray bursts or the random violence of an indifferent cosmos, though all of these are real risks, but destroyed by themselves by the specific failure mode of a species that develops the capacity for catastrophic violence before it develops the wisdom to constrain it. The Great Filter is a term that economist Robin Hanson introduced in 1998 to describe whatever it is that prevents a galaxy from being visibly filled with technological civilizations. It is almost certainly real. Something is filtering, because the evidence of absence, while not proof of absence, is far more comprehensive than the absence of evidence alone would suggest. The question is not whether the filter exists, but where it sits in the developmental sequence of a technological civilization. If the filter is behind us, if the emergence of life, or complex multicellular life, or of intelligence, is so vanishingly rare that our civilization passed through it and arrived here against astronomically low odds, then the silence is still complete, but it carries a certain grim comfort. We are alone because the universe made it hard to get here, and the worst is behind us. If the filter is ahead of us, if the sequence that ends in silence is a sequence from technology to the kind of technology that enables civilizations to destroy themselves, and then to destruction, then the silence is not comforting at all. It is instruction. It is the accumulated record of every civilization that reached this point and did not find a way through. The self-destruction hypothesis does not require a single catastrophic moment. It does not require a single decision, a single leader, a single triggering event. It requires only the failure to solve a coordination problem at the scale of a civilization, the failure to establish, before it becomes necessary, the frameworks and norms and governance structures that might prevent the physics of kinetic impactors and the logic of resource denial and the mathematics of communication delay from expressing themselves in the most severe possible form. The failure is incremental and cumulative. The satellite is jammed. The reconnaissance asset is blinded. The mining robot is disabled. The supply convoy is intercepted. The habitat is depressurized. The mass driver is turned outward. The impactor is launched. The orbital environment is salted. Each step follows the previous with a logic that is locally rational and globally catastrophic. And by the time the globally catastrophic nature of the trajectory is apparent to anyone with the perspective to see it, the trajectory may already be too committed to deviate from. This is not a comfortable thought to hold. It is not the kind of thought that makes sleep easy, or that allows the universe to feel like a place where the future is open rather than already written in the debris fields of civilizations that made the same choices we are beginning to make. But discomfort is not the same as hopelessness. The diagnosis is not the prognosis, and the silence of the cosmos, whatever its ultimate explanation, has not yet been interpreted to rule out something that the history of the civilization, for all its darkness, also contains: the capacity for cooperation under conditions that make cooperation appear impossible. Consider what it takes to survive in space, not to thrive, not to build civilization, not to project power across interplanetary distances, simply to survive. A human being in space, in a suit or a habitat or a spacecraft, is separated from instant death by technologies that require, for their continued function, an uninterrupted chain of cooperation among dozens or hundreds or thousands of people. The suit must be maintained by engineers who trust the manufacturing process. The habitat must be sealed by builders who trust the materials. The life support system must be operated by technicians who trust the procedures. The food supply must be managed by planners who trust the logistics. The medical equipment must be stocked and operated by people who trust each other's assessments of risk. Remove the cooperation and the person dies, not in a military sense, not in a political sense, in the biological sense that requires no metaphor and admits no negotiation. The environment will not pause the killing while the parties reconsider their positions. The vacuum does not grant extensions. This is not a weakness of space as a human environment. It is, potentially, its most profound strategic property, because the absolute hostility of the environment imposes a cost structure on conflict that has no terrestrial parallel. On Earth, combatants can destroy infrastructure and survive. They can deprive an adversary of resources and continue to access the same resources through alternative means. They can fight and pause and fight again in an environment that, however damaged by the conflict, continues to sustain the biological existence of all parties without requiring any deliberate cooperation. The air continues, the water cycles, the sun continues to rise. In space, none of this applies. A conflict that destroys shared life support infrastructure kills the people on both sides who depended on it. A conflict that damages water recycling systems in a shared habitat kills the people who share the habitat, regardless of their political affiliations. A conflict that renders a Lagrange point depot inaccessible through debris or weapons damage removes a resupply station that both sides needed. The hostile environment does not take sides. It applies its lethal indifference to everyone with equal precision, and it does so on timescales, minutes, hours, days, that leave no margin for ideological commitment in the face of a failing oxygen recycler. The International Space Station is, among other things, an existence proof of this principle operating under moderate geopolitical strain. Assembled over years through the contributions of 16 nations, including the United States and Russia during a period when the relationship between those two countries was characterized by significant mutual suspicion and occasional sharp confrontation. The station was maintained and crewed continuously for more than 24 years, a period that included the annexation of Crimea, the invasion of Ukraine, the sustained deterioration of U.S.-Russia diplomatic relations across every other domain, and the comprehensive mutual suspicion of two nuclear-armed states whose interests in almost every other arena were structurally opposed. During those 24 years, American astronauts and Russian cosmonauts continued to live in shared habitats, perhaps 800 cubic meters, dependent on the same oxygen generation system, the same water recycling equipment, the same supply chains, the same communications infrastructure, and to resolve, day after day, the operational disagreements and personal frictions and institutional miscommunications that arise whenever human beings share confined spaces and difficult conditions and differing priorities through the practical necessity that the alternative was not winning the argument, but both of them dying. The station is not a model of perfect diplomacy. It is not a demonstration that human beings are naturally cooperative or that geopolitical rivalry can be dissolved by proximity. It is a demonstration that when the cost of failure to cooperate is paid in the currency of immediate biological survival, and when all parties understand that the environment is indifferent to their political disagreements, the cooperative solution to even deeply adversarial relationships becomes, if not inevitable, then at least achievable in ways that pure political calculation would never predict. The Antarctic Treaty offers a parallel at a different scale, not a space environment, but an environment sufficiently hostile and economically significant that the major powers of the mid-20th century, during the height of the Cold War, found it more rational to set aside territorial claims entirely than to contest them in conditions that made economic exploitation impossible without cooperation. The treaty did not resolve the underlying geopolitical tensions between its signatories. It did not transform mutual suspicion into mutual trust. It created a legal and operational framework that made cooperation the path of least resistance in a specific domain, and that framework has held through every political change and strategic realignment of the past 6.5 decades, because no party has yet calculated that the benefit of defecting from it exceeds the cost of managing the hostility that defection would generate, in a domain where managing that hostility requires more cooperation than any of them can sustain alone. Space is not Antarctica. The resources are larger, the strategic interests are more acute, the communication delays are more severe, and the enforcement mechanisms are even more attenuated. But the underlying logic that an environment sufficiently hostile to all parties may create cost structures for conflict that push even adversarial civilizations toward cooperation as the dominant strategy is not unique to Antarctica. It is a general property of any environment in which the consequences of uncooperative behavior are borne, with particular immediacy and comprehensiveness, by everyone who depends on that environment, including the party that chose to be uncooperative. Space is that environment many times over. The vacuum is not merely indifferent to human suffering. It is indifferent to human allegiance. It kills the aggressor and the defender with the same calm precision. And that impartiality, terrible as it is in one sense, carries within it the possibility, not the certainty, but the genuine possibility that the species which learns to survive in it will be forced by the physics of their own environment to become something slightly better than they arrived as. There is no guarantee of this. The physics do not promise cooperation. They create conditions in which cooperation is advantageous. But history contains abundant examples of civilizations choosing catastrophically suboptimal strategies under conditions where cooperation was clearly the rational option. The logic of the prisoner's dilemma does not cease to operate merely because the environment raises the stakes. Sometimes raising the stakes accelerates a defection rather than forestalling it, because fear is also a function of stakes, and fear, particularly the fear that an adversary is about to defect, about to seize a resource, about to establish an unassailable position, is among the most powerful drivers of the preemptive strikes and escalatory spirals that transform manageable tensions into irreversible catastrophes. The outcome is genuinely uncertain. That is not a comfortable statement, but it is an honest one. The same civilization that assembled the space station under conditions of profound geopolitical tension also maintains, right now, the most destructive arsenal of weapons ever constructed, aimed at targets it has never fully stopped regarding as existential threats. Both things are true simultaneously. The capacity for cooperation and the capacity for self-destruction coexist in this species, as they have always coexisted. And the question of which capacity proves dominant in any given crisis is not a question that physics or orbital mechanics can answer. It is a question of choices, accumulated, incremental, compounding choices made by institutions and individuals and states who may or may not understand the full shape of what they are choosing. The species is young. This is perhaps the most important contextual fact in the entire story this journey has told, and it is worth sitting with quietly for a moment before the narration continues to its end. The universe is approximately 13.8 billion years old. The Earth is approximately 4.5 billion years old. Life on Earth has existed for roughly 3.7 billion years. Complex multicellular life, the kind with differentiated cells and organs and nervous systems capable of anything like cognition, has existed for perhaps 600 million years. Our genus, Homo, has existed for roughly 3 million years. Anatomically modern humans have existed for perhaps 300,000 years. Civilization, agriculture, writing, cities, the accumulated institutional infrastructure of organized social life, has existed for roughly 10,000 years. The Industrial Revolution, which created the technological foundation from which all subsequent development has proceeded, is approximately 250 years old. The space age in its entirety, every rocket ever launched, every satellite ever orbited, every human who has ever floated in microgravity above this atmosphere, spans less than 70 years. 70 years, against 13.8 billion years of cosmic time, against 3.7 billion years of biological evolution on this planet, against 600 million years of complex animal life, against the timescales of the stars, which burn for billions of years without hurry and die in processes that span millions of years and leave remnants that persist for billions more. By any reasonable cosmic measure, this civilization is not merely young. It is a newborn. It is in the very first moments of its relationship with the universe that surrounds it, still carrying the evolutionary programming of a species that spent hundreds of thousands of years competing for resources on a single savanna, still organized by institutions designed for populations measured in thousands and tens of thousands rather than billions, still reflexively territorial in a way that organisms whose survival once depended on defending a water source or a hunting ground are territorial. And it has just, in the cosmic equivalent of the last fraction of a second before midnight, developed the capability to extend those territorial instincts across a solar system. The trajectory is not written. The silence of the cosmos is not a verdict on what the civilization will become. It is an absence that could mean many things, and among the things it might mean is simply that the transition from a single-world species to a multi-world civilization is genuinely difficult, that it requires a kind of institutional and ethical development that takes time, that the civilizations which make it through that transition and persist long enough to be detectable are the exceptions, and that this civilization has not yet determined which category it will belong to. What the physics guarantees is this: the solar system is not going to wait. The resources that define the next century of technological development are there, in the permanently shadowed craters, in the low-gravity industrial potential of the belt, in the tidal energy of the Jovian system, in the water of Europa's ocean, in the gravitational geometry of the Lagrange points. The communication delays that will make Earth's authority operationally irrelevant at Martian distances and legally nominal at Jovian distances are going to arrive as reliably as the orbits that produce them. The first human beings born on another world are going to be born, and they will grow up in an environment that produces a different relationship to this planet than the one their parents carried in their memories. And that difference is going to express itself in the political and military arrangements of the solar system, whether anyone on Earth votes for that outcome or not. The only question that the physics leaves open, the only question where the answer is not already determined by orbital mechanics and resource geography and the speed of light, is what the civilization will have built in the interval between now and those inevitable arrivals that might shape the form those arrivals take. What norms, what institutions, what shared frameworks for managing the disputes that the physics guarantees will arise? What precedents, set in the first orbital confrontations and the first lunar resource conflicts, that would define the grammar of every subsequent engagement, for better or worse, for as long as human civilization exists in this system? That question is open. It is genuinely, consequentially, historically open. And the fact that it is open, that the window has not yet closed, that the first irreversible act has not yet been committed, that the debris fields and the silent weapons platforms and the locked orbital corridors are still hypothetical rather than actual, is, in the context of everything this journey has shown, something close to a gift. Not a comfortable gift, not a gift without cost, but a gift nonetheless. The gift of time, the gift of knowing, before the choices are made rather than after, what the choices will cost. Somewhere above this planet, right now, satellites are drifting through a darkness that is neither peaceful nor neutral. Their orbits are precise and patient. Their instruments, some open, some concealed, some pointed at the stars and some pointed at each other, are running on solar power and storing their observations in memory until the next downlink window allows them to pass what they have seen back to the people on the ground who sent them up there with specific questions in mind. Those questions are not all scientific. Some of them are strategic. Some of them are concerned with what the other satellites are doing and where they are positioned and whether their behavior has changed in ways that warrant a closer examination. This is not a new situation. It has been the situation since 1957, when the first artificial object achieved orbit, and every spacefaring nation immediately understood, with a clarity that the publicly stated purposes of civilian space programs never quite managed to obscure, that anything that could be placed in orbit over any point on Earth's surface. The orbital commons has always been dual use. The intelligence function of orbital space has always existed alongside the scientific one. The military has always been present, even when its presence was politely unacknowledged in the press releases. What is new is the scale, the number of actors, the density of the orbital environment, and the sophistication of the counter space capabilities, and the complexity of the dependencies, and the accumulating weight of unresolved questions about what is permitted and what is prohibited in a domain that the laws of the 20th century sketched an outline but never completed. What is new is the proximity of the moon as a strategic destination, and the funded programs to return there, and the specific absence of any framework capable of adjudicating the disputes that will arise when those programs arrive at the same crater at approximately the same time. What is new is that the question of the first space war is moved, within a single human lifetime, from speculation probability to something that careful analysts describe as a matter of timing and triggering events rather than fundamental possibility. And what is new is that the answer to the deeper question, not when the first space war will begin, but whether the civilization will develop in time, the institutional wisdom to match its expanding physical capabilities, remains genuinely uncertain, which means it remains genuinely open. There is no final answer to give here. There was never going to be. The physics and the history and the orbital mechanics and the resource geography have all been presented as honestly as language permits. The probabilities and the incentives and the precedents in the absence of adequate frameworks have all been laid out with as much care as the complexity of the subject allows. The story does not have a resolution because the story is not finished. It is beginning, and the ending is being written right now, in decisions made by people who may or may not fully understand the long-term consequences of what they are choosing. But there is something to say at the end of this particular telling. Something that belongs not to the analysis, but to the quieter register that underlies everything this journey has covered. The register in which the mathematics and the strategy dissolve back into the physical reality of what is actually happening in the world above the atmosphere. There is a planet. It is approximately 12,700 kilometers in diameter. It is wrapped in a layer of gas, nitrogen, oxygen, water vapor, trace quantities of 100 other compounds, held in place by gravity against the continuous gentle pressure of the solar wind. It has a single large natural satellite, a captured body of rock and ancient ice that raises tides in the oceans and illuminates the nights with reflected sunlight on a cycle as old as the solar system itself. It has oceans, liquid water, a condition so rare in the known universe that the catalog of confirmed liquid water bodies in the cosmos contains, as of this moment, exactly one entry. It has weather and seasons and the biological diversity of 4 billion years of evolutionary experiment. Every complex form of life on Earth descended from common ancestors, related at the molecular level to every other living thing on the planet, sharing genetic code with organisms as distant as fungi and trees and bacteria in the deepest ocean trenches. From the altitude of a geostationary satellite, 35,786 kilometers above the equator, the orbital altitude at which a spacecraft's period exactly matches the planet's rotation, and the satellite appears to hang fixed in the sky relative to ground below. The planet is a disk approximately the size of a large coin held at arm's length. It is blue, primarily. The oceans reflect back the sky's light with consistency that makes the planet's most abundant surface feature immediately apparent from the outside. It has swirling patterns of white cloud moving across its surface in the slow, complex patterns of atmospheric circulation. The continents are visible, not their political boundaries, which are invisible from this height, but their physical shapes, the coastlines and mountain ranges and river valleys and deserts that the geological processes for billion years have arranged and rearranged and arranged again, patient beyond any human accounting. At this distance, the planet is quiet, not silent. The electromagnetic spectrum is dense with signals rising from every major population center, a constant wash of radio and microwave emissions from a civilization that has been broadcasting its technological presence for over a century, without pausing to consider that every transmission carries a distance proportional to the time since it was sent, and that the most powerful of those earliest transmissions have now traveled more than 100 light years from their source, sweeping outward through a bubble of space containing several thousand stars, announcing to any instrument sensitive enough to detect them that something organized and technological arose at this location in the galaxy in approximately this period. But from geostationary orbit, looking down through the blue haze of atmosphere, the complexity of what is happening on the surface is invisible. The wars are invisible. The resource competitions are invisible. The satellite constellations maneuvering in the lower orbits are invisible, except as points of light moving against a fixed background of stars. The political arguments and the strategic calculations and the legal vacuums and the funded programs to return to the moon and the rocket factories preparing the next generation of vehicles for the interplanetary medium, all of it is invisible from this distance, compressed under 400 kilometers of atmosphere, and obscured by the scale of the planet that is, from this vantage point, simultaneously enormous and achingly small. What is visible is the Terminator line, the boundary between the day side and the night side, moving slowly across the planet's surface as the planet rotates. On the day side, the oceans are brilliant, and the clouds are white, and the land is green and brown, and the orange red of desert. On the night side, the darkness is lit at the margins by the faint glow of city lights distributed along coastlines and river valleys and plains where human civilization has been accumulating for the past 10,000 years. Small warm concentrations of organized light in a darkness that, from this distance, looks absolute. That line, that Terminator, moving at roughly 460 meters per second across the surface, dragging the day around the planet every 24 hours, has been doing this for 4.5 billion years. It moved in exactly this way before the oceans formed. It moved in exactly this way before the first cells divided. It moved when the first fish crawled onto land, when the first flowers opened, when the first mammal nursed its offspring, when the first human being looked up at the sky with the specific quality of attention that distinguishes our species. The capacity not merely to see the sky, but to wonder what it means, to ask not only what is there, but why it is there and how it came to be, and whether there is anything else looking back. That quality of attention, that wondering, restless, occasionally catastrophic, persistently hopeful intelligence, is the only thing in the observable universe that is known to produce the kind of questions this journey has been asking. The universe did not generate these questions anywhere else we can see, or if it did, the answers are not yet visible from here. This planet, this Terminator line, this thin layer of organized chemistry held together by gravity and sustained by a star of almost exactly average size and luminosity. This is where the questions arose. This is where the answers are being assembled, imperfectly and incompletely, and with all the difficulty that a young and occasionally self-destructive species must be expected to experience, but being assembled nonetheless. The first space war will begin, probably somewhere in the orbital commons that was never designed to be a battlefield, or in the darkness of a permanently shadowed crater where water ice has been sitting since before life existed on this planet, or in the silence of a Martian morning, in a conflict whose beginning will be described in a press release as a technical malfunction. The physics and the history and the incentives all point in this direction. The window for an alternative to that outcome is real, and it is closing, and whether it closes before or after something sufficient to prevent that outcome is built inside it is the most consequential unresolved question facing the civilization in the next century. But somewhere in the contemplation of all this, in the orbital mechanics and the kinetic impactors and the light hour isolation and the permanently locked orbital zones and the weapons that will outlive the civilizations that built them, there's also the planet, the Terminator line still moving, the ocean still reflecting the sky, The atmosphere is still holding, still cycling, still sustaining the astonishing and apparently unique biological experiment that has been running on this particular world for the better part of 4 billion years. The species looking up from that world is very new. 300,000 years is a moment against the timescales that govern the cosmos. 10,000 years of civilization is a breath. 70 years of spaceflight is a heartbeat against the age of the stars, against the patience of the orbits, against the scale of a galaxy that has been producing conditions for this experiment for longer than the Earth has existed. This civilization is at the very beginning of its story. The beginning is the hardest part. The beginning is when the choices matter most, because the patterns of the beginning are the patterns that persist, that compound, that define the shape of what comes after. Civilizations that survive their beginnings carry the fingerprints of how they survived them, in their institutions, in their norms, in the quality of restraint or recklessness with which they manage the first crises of their expansion. This is the beginning. This is the moment when the first satellites are watching each other in orbits above a planet that does not yet fully understand what it is doing. This is the moment when the craters of the lunar South Pole are being mapped with the specific attention of people who understand that their contents represent the first resource we're fighting over beyond the atmosphere. This is the moment when the physics of the Hohmann transfer and the 26-month window and the communication delay are just beginning to be understood by the people who will have to live with their military and political implications. And this is the moment when, somewhere in the quiet, a generation is growing up that will be the first to make the real choices. The choices that will determine whether the first space war is also the first step toward a solar system organized by law and norms and the forced cooperation of an environment that kills everyone who fails to cooperate, or whether it is the first act of the great filter expressing itself in this particular solar system, around this particular star, at this particular moment in the history of a universe that has been waiting in its patient and indifferent way to see which kind of civilization arose here. That generation is sleeping right now. Some of them are children. Some of them are not yet born. Above them, moving in the darkness at velocities that make the fastest aircraft look stationary, the satellites drift in their orbits, their instruments running, their orbits holding as reliably as Kepler's mathematics predicted they would. The Terminator line moves. The planet turns. The stars outside the atmosphere, the ones not lost to light pollution, the ones still visible from the dark places where the city lights don't reach, are where they have always been, at the same distances they occupied before there was anything on this world capable of measuring those distances. There is so much sky still to learn. There is so much distance still to cross. There are questions that the civilization does not yet know how to ask about the nature of the universe it finds itself in and the nature of the other intelligences it may eventually discover within it, and the nature of the long journey from a single blue world to whatever comes after a single blue world. Those questions are waiting, as the permanently shadowed craters wait, as the Lagrange points wait, as the interplanetary medium waits. Patient in a way that only physics can be patient, which is to say, patient without limit, patient without expectation, patient in a way that will outlast every ambition and every fear and every calculation of advantage that any generation of the species has ever carried with it into the dark. The only thing that cannot wait is the choosing. The only thing that has a deadline is a decision about what kind of civilization this one intends to be. For now, though, for this moment, in the quiet of whatever space you have found to receive this story, there's only the planet, turning slowly under its terminator line, and the satellites drifting above it, and the stars beyond, and the vast, unhurried silence of a universe that has all the time in the world, and is watching, in its patient and indifferent way, to see what the young species decides to do next. Rest now. The orbits will hold through the night. The mathematics will not change. The window is still open, and somewhere in the sleeping generation below, the answer is already forming, slowly and imperfectly, and with all the difficulty that any honest answer to a question this large must require, taking shape in the minds of people who will one day look up at the sky and understand, in a way we are only beginning to, how much depends on what they choose to do with what they find there.